Now. Welcome. Today's topic is DX piping for commercial split systems. Doug Baer will be your instructor. I, Ryan Hoger, will just be the eye candy without the visual. Now, I'll be reading questions off to Doug as we go. From a housekeeping standpoint, if you guys are attending for PDH hours, which I know some of you are, just make sure that you are logged in from separate computers. Like if there's two of you sitting in the same room, which is very rare now, but if you were, you each have to be logged in separately in order to participate. And occasionally I'll be popping up some poll questions just to get my proof to the state that you guys in fact were alive and attending. But with that, I'm going to turn it over to Doug.
Great, Ryan, thanks. Good morning, everyone. All right, so what we're going to do today in this webinar is we're going to go through refrigerant DX piping, as Ryan mentioned, for both our commercial split condensing units and remote barrel applications with chillers. So we're going to kind of dive into some of the basics, some of the outlines, and little troubleshooting with the piping for both suction, hot gas, and liquid piping, and some of the components and their effect. We will get into how to properly header multiple evaporators, and ultimately get down to the sizing tables, which you'll find very easy to read once we go through them. So with that, let's get started here. And again, we're talking about going, Ryan, you can see my cursor, correct?
Yes, we can.
Excellent. All right. So we're going to start today with the suction line. We'll go through that, some of the things we need to watch out for, how to size it, what it's all about. Same with the hot gas line. And then we'll get to the liquid line, and in this case you see a condensate line going into a receiver. We're not going to cover this today. Condensate lines and receivers, those are used in different applications other than the DX products we're talking about today. So those are basically an evaporative condenser type application. So some of the things we need to be aware of and concerned about with sizing pipe, designing pipe, laying it out is one, as you see, application, length of pipe, routing and obstacles, and of course pressure drop. Our charts are all about 2-degree equivalent pressure drops through the pipe, which we'll get into more clarification on that. And of course, oil return, liquid at the metering device, and ultimately protecting the compressor. So as I think everybody knows now, on this meeting here, that, 2 reasons for refrigerant piping, right? One, to handle the movement of refrigerant piping between the various components, the coils, the compressor, and whatnot. But 2, to also, in sizing, to also aid in returning the oil back to the compressor. Every second that compressor is on, there is a little bit of oil leaving the compressor, entrained with a liquid, entrained with a vapor, coming all the way back to the compressor again. So all of our vapor pipes, our discharge lines, our hot gas bypass lines, suction lines, all the vapor lines, that's where we have problems returning oil if our pipe sizing is incorrect or if there's issues out there with unnecessary traps. So we're going to cover all that little by little, and starting with the suction. So again, improper line size can cause floodbacks, slugging from oil, slugging from liquid refrigerant, loss of oil, overheating of the compressor if our pipe sizes are undersized, poor evaporator performance, flash gas at the TXV or metering device, low saturated suction temperatures. Just all kinds of things can arise from piping that's incorrectly sized and or routed. So in sizing pipe, regardless if it's a liquid, a suction, or hot gas, one of the things that we need to look at first and foremost when we're looking at the routing is what's the shortest distance between A to B, between the compressor, the condenser, to the evaporator, from the chiller to the barrel. What's the shortest possible distance? So in other words, let's keep it simple. Keep it short, keep it simple. That's rule number 1 with piping. So And sizing the piping, once we get into the tables, you know, we look at size. There may be two different size suction pipes that we could use, but we have to look at the friction rate. We have to look at the equivalent temperature pressure drop through it. So we need to look at that and look at the cost. So is it worth going to a smaller pipe to save the cost on it? And how much does that cost us in pressure drop and performance issues? So when you get into that balance, when there are a couple pipe sizes to use, you know, always keep your capacity, your performance in mind, as well as cost. So, of course, we always design for oil return in the vapor lines, meaning your suction and your hot gas lines. So fortunately, in the liquid line, we don't worry about oil return because oil is quite happy in training with the liquid refrigerant. It's the vapor state that we run into trouble with entrainment. So we'll talk about traps today. We'll talk about the liquid seal at the expansion valve, limiting the charge to 4 pounds per ton. This has been an old rule of thumb that's carried over from R22 into the 410 arena. And basically, we want to size our piping in distance and size. We want to stay conscious of how many pounds of refrigerant that means to the system. So when you see limits in our charts later on in the presentation of, say, 100 feet or 200 feet equivalent length or linear lengths, this calculation's already done. We've already looked at that before we put it in the charts to make sure that that length of pipe and the refrigerant contained within it equals up to 4 pounds or less per ton. So in other words, if you had a 10-ton system, the maximum amount of refrigerant that should be in circulation in that system is 40 pounds. Okay, so always look at your system charge total. And if you stay within our charts and our guidelines, it's a non-issue. It's when we want to go outside of that that we need to start doing the calculations of total system refrigerant. Okay, so that's what that's about. Of course, piping supports, we'll talk about that. Isolation valves and fittings for service. So, and of course, insulate piping where needed, which is obviously on every inch of the suction piping, as well as any kind of fittings or valves. You should try to insulate those as well. So again, maximum refrigerant pipe length, typically 200 linear feet. And as we talk and look at the charts today, we're going to see linear and equivalent lengths. So we'll have both. But on AC systems, split system condensing units, 200 linear feet is what you're going to find as the max length. If we're on heat pumps, typically they're 100 linear feet. If we're doing remote barrels or coolers on chillers, those are typically 75 feet. And there's some caveats there depending on what the product is. So, but your linear lengths, your max lengths, those are always going to be governed by the charts, which are in all the installation books per product by product line. Okay, so always follow. If you think you want to go outside of your total lengths in the charts, you need to contact us and let's talk about it. Let's see what we're doing. Let's look at the application, everything else. Okay. So most of our charts are going to have both linear length and equivalent length. Linear length is just what it says. It's a linear length between A and B, measured length. Equivalent length, we're adding in the fittings. So every elbow, if it's a short radius 90, a long radius 90, a 45, you know, whatever the fitting is going to have an equivalent length of pipe friction loss. So your equivalent length in feet have all the fittings calculated in. All the carrier charts and the Bryant charts, we use basically a 1.5 multiplier for our linear length. Okay, so we figure 50% for fittings. So that's already calculated in our charts. Just make sure when you're looking at the charts that you're understanding that you're in the linear length or the equivalent length. Okay. And most of the charts, pipe sizing charts, are in the installation instructions. With some products, we also have it in the product data. Always make sure you're in the most recent product data or the most recent installation instruction when consulting or going to the piping charts. So as far as the pipe itself, yeah, everything for the most part is copper in our DX systems. There's basically three types, the M, L, and K copper. And for refrigeration, for air conditioning, we're using the L and the K type. Okay, so that's basically everything we're going to talk about today. Now, there are steel pipe applications. We do have steel piping on the suction lines on some of our larger chillers. And again, if you're doing anything like that, you need to consult us because that steel pipe needs to be pickled. We can do the Vic fittings or welded joints, and then it's got to be cleaned up properly. So there are some guidelines if you're doing steel pipe on the suction lines on the larger chillers. I mean, we're talking, 100-ton plus chillers where we're starting to get into that type of pipe. But outside of that, for the balance of the day, we're going to be talking about L and K type copper on commercial split systems.
Doug, did you say
Yes.
steel pipe needs to be nickeled or pickled? I couldn't understand what you said.
Pickled, like you eat a pickle, kind of pickle.
So for laymen like me, what does that mean?
It's just it's a pickling, it's a treatment of the steel to make sure it's clean and free of all debris, particulate. Just a way of kind of treating the steel to make sure that it's, like I say, just it's clean and without particulate or debris on it.
But not with vinegar and salt like pickling.
Not exactly.
All
No.
right. Whew.
Not exactly.
I almost cleaned my system out here with that. All right, I'm good.
So again, as I mentioned a little bit earlier, one of our big concerns with sizing pipe is not only the refrigerant velocity and your actual friction loss through the piping, but also oil return. Again, oil with liquid refrigerant in our liquid lines, the miscibility is great. We have no problem in training the oil through the system in the liquid line. It's when we get into our vapor lines, our suctions and our discharge lines or our hot gas bypass lines, that's where we start getting into trouble and need to be, just right on, spot on your pipe sizing. So, and by pipe sizing, what we do is we maintain velocities. So typically our suction gases and our hot gases are traveling anywhere from about 500, 600 feet per second up to, you'll see 15, 16, 1800 feet per second. So we want to be conscious of the velocity of our gas traveling through the pipe. And that's part of what our charts are about. So fortunately, we don't have to go in and engineer all this nowadays. We can simply go to our charts and figure out what we need. Okay, so that's the good part of where we're at today. But just pointing out these things so you know how we got to the design, to the pipe size, and why we do what we do with risers and everything else, which we'll get into detail in a bit. Okay, so just remember our vapor lines are the ones we really need to look close at. Liquid lines, we want to keep them as short as possible, of course, and we want them to be sized correctly because undersized piping can cause capacity loss on all three lines, your liquid, suction, or discharge. So we want to make sure that they're sized correctly, and on our vapor pipes that they're not oversized, which would slow the velocity down of the refrigerant and we'd lose the entrainment of the oil. So pipe sizing is very critical. So some of the typical layouts that we run into or orientations, we have the condensing unit and evaporator coils on the same level. We've got the condenser above the evaporator. We've got the condenser below. These are all things to think about, especially with traps and liquid lift, things like that. So typically on the same level, you can go straight from the condenser right to the evaporator coil or the cooler if it's a chiller. Okay, you don't have to have this inverted trap, but it doesn't hurt to have an inverted trap. And typically when you run inverted traps, you're going to take your suction equal to or slightly above the evaporator coil. Okay, and all that is to keep the refrigerant back here in the coil on the off cycle. You know, if we don't have that trap, we could have the refrigerant, depending on migration from temperature, making its way back to the condenser, you know, causing some flooded starts. But all of the equipment, and this goes for all manufacturers, everybody does what's called flooded start test. So we know how much pipe we can have on the system in what arrangement or orientation without doing damage to the compressor. So flooded starts are something that everybody looks at as far as manufacturers go. Okay, so the same level again, you don't need any trap. If you happen to have an inverted, that's okay. What you don't want is any kind of J trap or P trap that can cause oil to store out in it, and we'll get into more detail as we go here on that. With the condensing unit above the evaporator, there's no need for any traps at all. Now, back in many years ago, you get into refrigeration, we used to have what were called lift station traps. So calling the line right here a suction, used to go up about 10 feet, there was a trap, you go up 10 more feet, and there was a trap. And what that was for is as the oil traveled up, it'd fill into the trap. Once the trap filled up with oil, then it would blow up to the next trap, and it was just a lift station trap system that allowed us to get the oil back up to the compressor. Now, that was mainly refrigeration duty. I think the Train may have done that for some time in their DX splits. At Carrier, we've never done that. We've gone to either speed risers, which is a downsized suction line in the verticals, or we've gone to double suction risers, which I'll get into more detail and show you the charts here in a little bit. Currently, no traps at the top of a condensing unit. So when I say condensing unit, I'm talking about a compressor bearing condensing unit. If I was talking about a condenser only with fans, that's another story which we'll catch up with today also. Okay, so the other application is when the compressor or the condensing unit is below the evaporator. When you have this orientation, you always want an inverted trap on the suction, and that trap needs to go equal to or slightly above the top of the evaporator. And what that is again for off-cycle migration. The unit shuts off, and we don't want any of the refrigerant in the suction or the coil rolling back down to the service valve or the compressor waiting for it to start. So this is the only trap that you're going to have when the compressor or condensing unit is below. Will be an inverted at the coil, and this applies back, all the way down to the residential equipment. Same thing. Residential equipment is the only time you're going to see a trap. Residential equipment, you'll never have a trap when the condensing unit is above. There's no reason for traps. We don't need speed risers, and we don't need double suction risers in residential equipment up through 5 ton. Okay. So these are kind of the typical orientations that you run into out there, and sometimes you have a combination of. Sometimes we have piping that comes out, the units are on the same level, but piping comes out, it's got to go up, over, and back down. And that's the same level system, but you may get into needing double suction risers or speed risers like you would in this application. If your suction's coming out, going up, across, and back down, even though the units are at the same level. So always look at your piping and think about flow, think about vertical lift, think about vertical rise for suction, and think about, well, we'll get into the hot gas, I'll explain that, it's a little bit different, but basically the same theory as suction pipe. So again, keep your piping simple. Avoid any kind of traps, unnecessary pockets, going underneath beams. We run into that actually pretty often. I'll see jobs, people will submit some proposed piping to us for us to size. And I'll see the pipe runs come over, and we have a pocket or beam area. We drop the pipe down. I've seen them run over as far as 20 feet and back up. Well, guess what that just formed? Whatever your depth is here, say it's 12 inches, you got a 12 by 20 foot trap here. And just a lot of area for oil to sit there when the compressors or system is at low capacity, low load. So we need to think about that with pipe sizing as well. And again, when we get into the charts, I'll talk about that a little bit more. Okay, so avoid unnecessary traps or pockets. Always allow for expansion and vibration of the piping. If we took this pipe, we ran it straight from this point to this point, you get into the larger copper piping, that pipe moves as it gets hotter or colder. And when it gets hotter, if it's a discharge pipe and it's got no place to go, you end up getting fractures at the connection points, the manifold points, other points. So always think about expansion when we're doing long pipe runs. Think about expansion in the vertical runs, think about expansion in your horizontal runs, and allow for that. So a lot of little details just in the initial thought process and layout of pipe. And you may see this a few times through this whole presentation today. Do not bury the refrigeration lines. There is no application or suitable method that's allowed nowadays for buried refrigeration lines. The problem is when you think about the condensing unit outside in the ambient temperatures, let's say it's a 70-degree day. I wish we'd have one of those soon here, but let's say it's a 70-degree day. So the condenser coil, the whole condensing unit, it's roughly at about a 70-degree temperature. Your evaporator coil is in the airstream. We're going to assume the building is, 60-some degrees, 70-some degrees, maybe a little warmer. And now we have this buried piping that's in the ground that's typically anywhere from, say, 52 to 60 degrees. Well, as we all know, refrigerant always seeks the coldest location. So what you get is all this migration into the piping that's in the ground. As far as the liquid line goes, that's not an issue. But the suction line is. So think about your suction line buried in the ground and all the refrigerant migrating to that point in the off cycle. Now you've got a column of liquid in that suction pipe. The compressor starts up. We draw that stuff back. We start slugging the compressor. We start washing the bearings of oil, just all kinds of damage to the compressor. So we don't have any given length you can use. The way it is nowadays is just don't bury it. I've had multiple people come to us and say, well, I've got a 12-inch PVC chase that's buried in the ground. I put crushed stone around it. It's 3 foot deep below the frost line. Took all these precautions. It doesn't matter. We still will end up with migration. The units nowadays, everything we have now are typically scroll and screw compression style units. The oil that's in the systems now are half of what we used to have in the semi-hermetic compressors. So the oil management becomes a real problem too, not only liquid slugging, but oil management because of the migration. So we just don't allow buried lines anymore, no matter how you do it. Receivers, accumulators, all these little added refrigeration specialties don't solve the problem. So again, just don't bury refrigeration lines. We won't support it. The factory won't support it. Most of the manufacturers are in that same mode right now. Just no buried lines. It causes too much trouble. So hopefully I beat that to death for you, and you understand what our opinion is on it. So getting back to suction line design now, let's talk about suction lines. Again, keep it short and simple. Suction piping is typically designed for an equivalent 2 degrees line loss. So think about 2 degrees Fahrenheit and think about what that does for your pressure on whatever given refrigerant you're working with. So 2 degrees in R22, 2 degrees in 410, 134. What's that? That's your equivalent pressure drop measured in temperature, okay? So that's typically what all of our charts are set up for. I'm going to show you some other charts later today on some of our smaller condensing units, the little 6 through 15-ton units. Talk about that, and there you'll see a couple other pressure drop numbers, but you want to at least be around 2 degrees or less, but you can design at 3 degrees just understand you're losing certain percent of capacity out of the machine. And we'll get to more detail when we get to that slide later on today. Okay. So suction line, you want to always pitch the horizontal runs an 1/8 inch per foot in the direction of flow, which is always going to be going back to the condensing unit or the compressor. Double suction risers where required. We'll get into that in their design. Or speed risers, and we'll talk about that and where you use them. So, and again, avoid traps. We don't want any intermediate traps in the risers. We want either speed risers, which typically is a pipe that's one nominal pipe size smaller than your main suction run. And we use those at a 3-foot distance or less in the verticals. If you're over 3 foot, then we go to double suction risers if required. Okay, so we'll get into when they're required and how that's decided in a bit here. You want to think about isolation when running pipe. You know, you want to have it properly supported, but you also want to think about isolation. Back in the day with the semi-hermetics and recip compressors, you know, the frequency range in which they operated in was a lot less than today's modern screw and scroll compression units. They tend to set up a different frequency or vibration in the piping, and you sometimes have to accommodate for that. So think about how you're mounting it, where you're mounting it to. You know, you don't want, you know, you're going to have some vibration out of all pipe with refrigerant and, you know, attenuation of compressor noise. So be careful the structure that you're mounting it to, you know, the walls, just like residential. You know, you need to watch your penetration through the side of the house. You want to watch where you strap the pipe to so it doesn't attenuate into the walls or the ductwork. And commercial is the same thing. You know, be conscious of what you're, you know, what you're fastening the pipe to, and think about isolation. Now, we don't call out vibration eliminators on our equipment. If you want to use them on the carrier equipment, Brian equipment, that's okay. Just make sure they're full port. In other words, the ID is the same exact ID or larger than what the pipe size is. But you can use those. We just don't call it out in any of our manuals. Okay, so think about your mounting too, not just your equal spacing, you know, your 3 or 4 foot spacing on the pipe, but think about the structure you're mounting it to. We'll talk a little bit about TXV bulb location. Talk about multiple circuit evaporators coming up here real soon. And did I mention not to bury refrigerant lines? I'm not sure. If not, don't bury them. Okay, not allowed. Accumulators, we'll talk about accumulators on the condensing units. When we're in a long line application, and we'll get to that. Typically, it's at 100 foot or more commercially. Or we're VAV, variable airflow, variable air volume, or VVT applications. Typically, we'll have accumulators on the units. Now, you can also field install accumulators. You know, we'll get into a little bit of that. Most all the accumulators we use, and this really goes back to our R22 days and our 38 AHs, our AKs, a lot of those units. We got into field installed accumulators. All of them that we use are typically the vertical style, so they sit in a vertical position. You can get horizontal accumulators that do the same job. But again, consult with us first before you install accumulators. Most of the time, you shouldn't need them, but there are some applications with VAV or VVT that you know, we can put them on. Now, a lot of the units nowadays, you know, if flood and start test didn't pass, they come standard with accumulators. So, but again, get a hold of us. We just a quick explanation of pipe sizing. All of our TEC customers that do piping, we always look at the pipe layout and the pipe sizing for them. Okay, So if you're doing a commercial job, what we need from you is a drawing. We want the proposed routing, proposed drawing. Of course, we'll get the schedule of equipment from our submittals from our sales team. And with that, we'll go in and tell you what size pipe you need and, you know, risers, how to construct them. If you need an accumulator, we'll go through all that, tell you what your refrigeration specialties are, you know, from TXV to filters, you know, whatever you need help with. So it is a service that we do through tech support. So again, give us a call if you're thinking about mounting an accumulator, if you're putting one in the system, if you're doing anything different than what the book says or in links, please give us a call and let us work with you on that. Okay. So let's talk about the evaporator and manifolding of evaporator coils. So a couple things with DX cooling, especially when you get into VAV or VVT applications. So any kind of variable air volume or temperature applications, we have to have what's called full face active coils. So here we have an upper coil and a lower coil. By full face, that means both coils need to be active during operation. Now there's what's called split face, and that would be if this coil was running independent of the top coil. Now, usually split face applications were something where there was some type of humidity process control. Other than that, there isn't any real comfort cooling practice or use for split face application. Because let's think about it. We're trying to cool and dehumidify the air, right? If only the lower coil is active, then this whole upper coil, we have bypass air through it that's unconditioned. So we just aren't getting the humidity down quickly and the temperature down quickly to control the space for comfort type cooling applications. Now, you get into process applications and you get into some split face stuff, okay? So if you do, and I'll just cover this real quick, if you get into a split face application, the bottom coil will always be the first on coil and the last off coil. So this is the first one to have its solenoid valve energized and have refrigerant flow, and the last one off. And the purpose of that is, if we brought this one on first, the top coil, think about all your condensation. Your condensation is going to run down and run onto a warm face coil, and it's not going to hold the condensation. You'll get condensation carryover, blow off, whatever you want to call it. So that's why we always have first on, last off on the bottom in split face applications. Okay, so going back to comfort cooling, full face application, but we can get into multiple circuits. Here we're just showing a single circuit on the top, single circuit on the bottom. In reality out there, we typically will have a row split coil. So we have one circuit on the entering side, we'll call this the entering side. So we'll have one circuit on the entering side, we'll have one circuit on the leaving side of each coil, which if we had that here, we'd have two TXVs feeding the upper coil, two TXVs on the lower coil, and of course, 4 suction pipes. Well, when we have that, this is how you combine it. We combine the circuit on the bottom, the circuit on the top. In a row split coil, meaning if we drew a line or cut right down through the middle of the coil like this, that would be row split. In that case, the leaving side of the coil circuit, which would be this side, because I'm saying airflow is going this way, this side of the coil would be your first on circuit, last off circuit, for the same reason, for condensation management. If you brought the back or entering side of the air entering side of the coil on first, then think about that. We're generating our condensation back here. As air travels through, we carry the condensation through, gets to the warm side of the coil, and it just spits off. We don't hold on to it. Okay? So always think about airflow when we're manifolding the coils together, and think about your first on, last off circuits. If you have a row split, again, row split would be like this, up and down, or if you have a phase split for any reason, okay? Think about which one's on first or last, okay? In piping these coils on the suction side, one of the first things we want to think about when we manifold together is, are we properly draining that coil? So we always want to think about the oil that's in the evaporator coil. So again, you know, the oil's being carried from the liquid pipe out of the compressor through the liquid pipe to the TXV. We get into the coil, and depending on what our load is, depending on what our capacity is, maybe we have a 3 compressor circuit and only 1 compressor is running. So now our capacity is reduced, our refrigerant velocity is reduced, the oil starts dissipating out. Well, we want to make sure that any oil that accumulates in the evaporator is properly drained into the suction line. So think about your stub outs on your suction header and how you're going to pipe that. So you want to get that as low as possible before we start taking it up on our risers and our manifold and connect those together in your main run back to the compressor or circuit. Okay, so think about the draining of the coil as far as oil goes. Now, this is kind of a self-draining coil. There are other coils with your suction header where your stub out may be at the top, it may be in the middle. And typically those coils will have a drain line down here that will connect to the suction line, which is what you see right here. If you look at that right there, that's an oil drain line. But typically, you'll know that there's an oil drain line if the suction stub out is, like I say, at a middle point or somewhere up higher on the header. So always be conscious of getting the oil out of the coil. Okay, so that's number 1, thinking about suction piping headers. Number 2, we need to think about the TXV sensing bulb mounting point as well as the equalizer tube. So think about that. Now, for drawing's sake, that's just where this equalizer tube ended up. Don't ever put the equalizer tube in an elbow. You want to have it somewhere near the sensing bulb, a little bit before the sensing bulb, but in the same area. Okay. The mounting of the sensing bulb while we're looking at these headers is something to think about as well. The sensing bulb, in this case, in the vertical position, on the vertical section of pipe, the sensing bulb itself has a right side up, upside down mounting, right? We always want it right side up, meaning that as the bulb is mounted onto the pipe, the capillary tube is coming out of the top of the bulb. You never want to turn this upside down where the capillary tube's coming out of the bottom of the bulb. These bulbs have a refrigerant charge in them, and there is some liquid refrigerant in there. So picture if you turn this upside down where the cap tube is coming out of the bottom, now that liquid is sitting right on that opening, and we just don't get as smooth a control back to the power head of the TXV because we're trying to push liquid through the small capillary tube. Okay, so we should always be in this position so the liquid refrigerant in the sensing bulb can boil off in a vapor state and allow pressure change back to the power element that way. So think about how the bulb's mounted on the line. If it's vertical, a vertical pipe, obviously, you know, doesn't matter what side you put it on the pipe, but it does matter where you put it in relation to the suction header. So basically the rule of thumb for a TXV sensing bulb is 290-degree elbows away from the suction header. Now in our books, and I've got some pictures coming up, we're going to give you tube diameters, 8 diameters horizontal, 15 diameters up, meaning whatever the diameter is of the pipe. Let's just, for round numbers, let's say we have a 1-inch pipe, which we don't have 1-inch refrigeration pipe, but for easy math, let's say it's 1 inch. Well, we want 8 diameters out. Well, 1 inch would mean 8 inches out, and 15 diameters up means 15 inches up. So when we talk about pipe diameters, 8 pipe diameters, 15 pipe diameters, that's what we're talking about. Now, that's in a perfect world where we have room, in the manifolding of the suction lines. We've got room to mount our sensing bulbs in these, dimensions. If you run into short stub outs before you hit the manifold, at least get 2 90-degree elbows in the pipe before you mount the suction sensor, the TXV sensing bulb. And we're going to call these 90-degree elbows mixing 90s. So what that does is it takes the accumulation of all the tubes, suction tubes going into the suction header, and it allows all the different temperatures of suction gas that we're going to have to mix. So you get mixing 90 here, you got a mixing 90 there. Hopefully by the time we get to the sensing bulb, all these different temperatures coming off of the suction header will be in one mixed common temperature state. So sensing bulb location, things to think about, you know, don't mount it upside down. 2 mixing 90s. And this is when you're going in the vertical. Now, if you mount the sensing bulb in a horizontal section of the pipe, we've all heard about that 4 o'clock, 8 o'clock position. Doesn't mean you couldn't go to 3 o'clock or 9 o'clock. The biggest thing about those positions when you see that on a horizontal pipe is you don't want it mounted between 4 and 8 o'clock on the pipe, in the horizontal section. And the reason is that's where all your oil is returning. So the oil is going to be laying down on the bottom. And if you go from the 4 o'clock over to the 8 o'clock position, that oil is going to act as an insulator, and you may not really be seeing the proper refrigerant temperature you're looking for with a sensing bulb. So when you see that 4 and 8 o'clock position, or you know, a 2 and 10 o'clock, basically anything below that. Think about oil, think about gravity, think about where all the oil is returning. Now, of course, there's oil suspended in the refrigerant vapor, and coating the walls, but a lot of that is going to be at the bottom of the pipe. So always think about that. Think about the insulating factor when locating the sensing bulb. Okay. So the pipe right here coming off your headers, whatever your header stub out is, the easiest way to do this is whatever the header stub out is, that's what size pipe you should use in your header assembly before we bring them together in the main suction pipe back. Okay, so this is coming off 7/8, then this should be 7/8. This is coming off 5/8, it should be 5/8 until we finally collect in the main suction run back. Now, we may have instances where these distances here require double suction risers. And we'll get into how we determine if we need to do that or not in a little bit. It's all about a chart that gives us oil entrainment at minimum tonnages. And we'll go through that and it'll make a little more sense. But easiest way is always think about what your stub out size is and stay with that until we collect either in a double suction riser or up here in the main pipe back. Okay. Off-cycle protection, what that's referring to is the inverted trap. Okay. When you come off of your header, you come up on your risers, you want a little inverted trap here and here. So we don't want any oil, residual oil up here on the off-cycle running back down, sitting down here in the bottom. Okay, we want to do everything we can to help that oil get back to the compressor in every stage of the piping. Okay, so let's think about that. And of course, your main line back, your main suction line, that's always going to be pitched back to the compressor an 1/8 inch per foot. Okay. As we get into the piping in a little bit with double suction risers, we talk about an A pipe, we'll talk about a B pipe, and we talk about a C pipe. Your C pipe is always the main suction pipe run back. That will always be your C dimension. When we get into double suction risers, there's going to be an A pipe dimension and a B pipe dimension. When we get to those slides, I'll get that clarified. Okay. Ryan, any questions on this so far?
Yes, we do have a couple questions. And while I'm reading those to you, I'm going to launch one of the poll questions. Anyone's allowed to answer them. It's totally fine. In fact, it's more fun if you do. But if you need PDH hours, you definitely have to answer the questions. All right, so let me pop up this very first one. The question is, which is not a typical recommended design guideline? Your choices are going to be A, keep the piping under 200 linear feet. B, keep the condensing unit above the evaporator. C, limit the charge to 4 pounds per ton. Or D, design for oil return in the vapor lines at minimum load. So I'll let you guys answer that on the screen while I read some of these questions to Doug. One of the questions was, is the piping design assistance from TEC at an additional cost? Or is it?
No, that's free to all of our customers. So if you have an account with us, it's a free service to you.
Yep.
What you do is you work through your sales TM, your salesman, and of course you'll have the submittal, which will tell us what the equipment is. You'll provide us with a drawing It doesn't have to be a CAD drawing, but preferably something better than a napkin with coffee on it, right? Something legible. So what we want is your total linear distance. We want any vertical elevation change. So if you can highlight all that with dimensions in preferably feet, but if you're SI and want to do it in meters, that's fine too. I can break that down, but preferably in feet. But give me the elevations, number of turns, just a rough sketch to a CAD drawing, anything like that. Okay. So once we get that, we have the equipment. My salesman will give us the submittals on the evaporator coil and the condensing unit, or the chiller and the remote barrel. And from there, then we can kick back to you the pipe sizes, if you need double suction risers, if you need double discharge risers, and what their A and B pipe sizes are. So we provide that to you. We'll also tell you what size TXVs to use, because some of these commercial jobs, it's not unusual to see 4 TXVs, 8 TXVs. You get up to the 100-ton, 130-ton range. 8 TXVs are common. So there's a lot of stuff going on there. It has to be correct. So we'll do the TXV sizing for you, as well as the nozzle sizing, and I'll get into the nozzles a little bit later too.
All right. For those of you guys answering the poll question, 2 of you have typed in that you can't click on it. I don't know what's going on with your computer in that regard, but 63% of the people have actually selected an answer. So I'm going to close the poll right now, and we'll shut that down. I'm going to do one more right now since we're a little behind, and then I'm going to ask Doug a couple more questions that you guys typed in. So this one is, which piping material is not used for HVAC refrigeration? Copper K, copper L, copper M, or steel. So pick one of those. All right. Other questions, Doug? In regards to the base split arrangement and the row split arrangement, did you say it was the bottom coil on face split is first on and first off, and then on row split, the discharge side of the coil is first on and first off?
Okay, so again, we'll look at this coil right here. We'll call this the lower coil, this the upper coil. If it's face split, which would mean you draw a line across here, and meaning this coil will come on first, this one will come on second. So the bottom coil is always the first on and last off. So this one would start first, the bottom would start first, then the second one would start, the upper coil, then the upper coil would shut off, and then the lower coil would shut off. If you're row split, then we're going to say our air is traveling this way. So this is our entering side of the coil. Over here is our leaving side. The leaving side of the coil in a row split arrangement, this will be your first on and last off. Okay, first on, last off. Now, what I didn't mention is a lot of our coils come out intertwined. So an intertwined coil, if you've got dual circuits, there is no first on, last off concern, in a row split arrangement, because they're intertwined. Doesn't matter, but always make sure of what you've got if it's intertwined, and we can tell you that. We'll tell you, but I'm going to say that probably 90% of the coils that we select for you or build for you are intertwined coils now. So the only thing you need to make sure of is you're not doing face split right here. Okay, so we want both coils active all the time, through your intertwine or row split setup.
All right,
okay.
That makes sense.
Right.
For those that were answering the questions as we were going here, in regards to the first question that we had asked, the answer that did not apply, that didn't fit in, was keeping the condensing unit higher than the evaporator. You don't have to do that, obviously. The other answers were all legit. For the second question, which we had asked, which is the piping material, the copper M was the inappropriate material. Copper K, copper L, and steel are all good to be used for refrigeration. I think we have all the questions. Everything else everyone typed in is because they couldn't figure out how to use the poll. which is weird because that never comes up in these things. But apparently people didn't have it in the full screen mode. It was what some of you guys are saying. So you must have had it like minimized into a little box in the corner or something. If you're in the full screen mode, or you can't click on it when you're in the full screen mode. So maybe that just helps some of you guys that were having trouble answering them. And with that, I'm going to stop blabbering and let Doug continue on.
All right. So some more pictures of coils. These are what you'll find in our both in the product data and installation manuals. This is for our commercial 20-ton and up split system condensing units. So we've got multiple pages. I just happen to grab this one that will give you some guidelines on piping of the coil. So here's a picture of a free drain coil. You can see your suction stub outs coming out of the bottom of the header. Here's a picture of a non-free drain coil with the oil line coming out of the bottom of the suction header. Now, probably 95–98% of the time, we're always going to supply you with a free drain coil. It's not till you get up to 75 to 100 ton and up where we start getting into the possibilities of going into a non-free drain coil, and then that'll be marked out for you as well. We'll start getting into now some of the double suction risers and the double suction riser construction, which is right here. When we talk about double suction risers, the smaller pipe is always going to be your A pipe. This will always be the B pipe. And remember over here, your main suction run back is the C pipe. So when we look at the charts here in a little bit, you're going to see A, B, and you may see C on some of our charts. Now, when you make a trap, when you make the trap for your double suction riser, you want to make this as short as possible. And as they say here, use like a 45 and a 90 street L. So you want this trap as small as possible to hold as little amount of oil as possible. And how these work, we'll say we're running at 100% capacity right now. Let's say we've got a 100-ton unit and we're running at 100 tons capacity. Well, we've got enough suction velocity to entrain both oil and suction gas up both the A pipe and the B pipe. But now let's say we start unloading the machine. We've got a 100-ton machine, and this guy can unload all the way down to 7%. So it's going to get down around 9 to 11 tons. Now all of a sudden, these pipes become too large. Your main B pipe becomes too large, and we can't maintain our velocity up the pipe. And because of that, the oil dissipates out and won't return. So ultimately what happens is this trap fills up with oil, blocking this pipe off, and now all your suction gas and oil coming out of the evaporator coil now starts entraining and running up the smaller A pipe to collect in the main suction back. So again, if a double suction riser is called out, which we'll see in a little bit where it's called out, if it's called out, it's anytime you have more than 3 feet of vertical pipe. So if I'm only going up 3 feet here, but the unit's calling for double suction riser, I don't need a double suction riser. I can use what's called a speed riser, which is a 1 nominal pipe size smaller pipe. Okay, so let's say I've got a 2 5/8 suction line. That means I would drop down to 2 1/8. If I had a 3 1/8 suction line, it means I drop down to 2 5. So you kind of get the picture there. So in that 3 foot distance, we can use a speed riser, but as soon as you get past 3 feet, then you have to construct the double suction riser, provided again that a double suction riser is even called out in the piping chart. And I'll show you where that's at in a few slides here. Okay. So multiple drawings in the books. There will be applications that you run into where you've got 4 TXVs, 6 TXVs, 8 TXVs. I had a job with 12 TXVs. You're going to get into that stuff in the larger commercial stuff, the larger commercial equipment. When you do, that's where we need all the information. If you're providing the evaporator coil, we need all the build data on that. We'll get the equipment submittals, and I'll have that part, and then I need your pipe drawings, and then I'll be able to give you some drawings back of how to manifold all the suction stub outs together, how we manifold the liquid, how we do all that, and your TXV sizing, because it gets you get into a 12 or 8 TXV manifolding job, and you know it's an hour's worth of work. Easy to get it right and get everything calculated out. So, but just like I say, get that over to us, and we will help you through that. So again, I think we already covered this. TXV location, again, if space limit is limited, make sure you have at least 2 mixing 90s before you mount the TXV bulb. In our books, that's where you'll see minimum 8 diameter, minimum 10, minimum 15 diameter, and I explained already what was going on there. So that's what that's all about. Now, some of our larger air handlers, as you see the stub outs right here for the pipe, it's typically not how they come. They will come with just a blank door on the air handler. So you have to make the penetration through the door for your liquid and suction stub outs. Okay. So just a point there in the slide. So talking about sizing the pipe, actually getting into the pipe tables now and looking at what we need to run if we need double suction risers. One of the things that we do when we design or determine if we need double suction risers is based on the unloading capability of the machines. So like I mentioned earlier, a 100-ton machine, those things unload down to, 11%. Some will unload down to, 7%. So you think, hey, I got a 100-ton machine. Well, that thing can get all the way down to around 10 tons, 9 tons. And we've got possibly 2 5/8 pipe on this machine, or 3 1/8 pipe, and all of a sudden now we're only connecting or running at 10 tons. And now you can start to see, hey, I've got a grossly oversized suction line. So we can handle it in the horizontal areas, but it's the vertical areas that run into trouble on the suction side with oil entrainment and return. Okay, so we have a lot of different setups in our units. We have single compressor on a circuit, where each one runs at 100% per circuit. We have tandem compressors on a single circuit. We may have 3 or 4 compressors on a single circuit. And of course, they don't all run at the same time. So in a tandem compressor circuit, if this one's off, you're only running 50% capacity, not 100%. So we look at the 50% capacity, and what does that mean? 50% of what? 50% of a 50-ton, 50% of a 20-ton. The math is simple to calculate, but we need to know what those minimum tonnages are to address our vertical sections. Okay. If we have the old semi-hermetic compressors, we could have 1 head with an unloader. We could have 2 heads with an unloader if it's a 3-head machine. Okay. So this takes off 33% of the capacity. The other head takes off 33% of the capacity. Now we're left with 33% on the center head. So we've got 30% basically, or 33% actually trying to return the refrigerant gas through the suction. And at that point, the piping would be oversized. So again, that drives you to look at your verticals and if we need speed risers or double suction risers. We've got 2-stage compressors, same thing, 100% or 50%. And moreover now, we've got the digital scroll compressor. So this kind of throws a whole new curve to us. These compressors, digital scrolls, now they don't unload like the 2-stage compressors, where that unloads internally and unloads 50% of the scroll flank area, or the old ones where we disable, a couple of the pistons in it. The digital scroll compressor is either pumping at 100% or it's pumping at 0%. So as you see, the stationary scroll flank lift, when it lifts, that's 0% capacity. When it's down, we're sealing the 2 edges here and we're pumping at 100%. So scrolls are either 100% capacity or 0. So when we look at the unit and the available tonnage for minimum oil entrainment, we look at what this compressor does at 100%. So it's either pumping or it's not. So you look at the compressor tonnage, not necessarily the percent of capacity of the entire condensing unit. So let's say we have a 38A PD, which is a dual circuit carrier condensing unit. That's a 38A PD 100. Okay. We can go down to, 11, some units we can go down to 7%. And do we look at that particular tonnage? No. What we do is we look at the A1 compressor, which is your first on, last off compressor, and we look at what tonnage that is. Well, if it's a 10-ton digital scroll, a 15, 20-ton digital scroll, we look at the tonnage of the scroll itself because it's either 100% or it's not. Okay. And what we do electronically is, of course, we're looking at multiple things: saturated suction temperatures, pressures, discharge pressures, temperatures, number of condenser fans running. We look at the whole picture of how the machine's performing, and then we unload the compressor for further capacity in increments. So it's how long it's unloaded, how long it's loaded. So in this case, we got 7 seconds where it's loaded, then we unload for 8 seconds, then we load for 7 seconds, and that's, if you've ever heard one, you can hear them loading and unloading. So that's how we're taking control of capacity. So when we're at 100%, obviously we're returning oil, we're giving the full whatever 10, 20, 25 horse or ton capacity. So it's a little bit different than just figuring the sheer percentage of capacity off the entire machine. Okay. So always think about that on digital scroll. Don't go to, hey, if I'm unloaded for 10 seconds and only loaded for 6 seconds, I'm at this percent. You don't do that. You look at what the tonnage is of the compressor itself. Okay. Is that clear? Any questions on that?
That was clear. There are a few other questions on, I think, the last slide. There was that 2-stage scroll that you had, maybe one more back. There was that 2-stage scroll and you had it listed as 50%. Although a lot of our systems, it's usually like 60 something or 70 some percent. Do we have ones that are 50% and others that are 70% when you unload it?
No, just for the slide.
Okay, so there is no 50% option. When we unload to stage 1 of a 2-stage scroll, we're going to get like 68, 70, 72% or something like that.
60, 66%, right.
Got it. Okay. That's helpful.
Yeah, just for kind of pointing out the extremes.
Got it. Some of our rooftops, we have 2 unequal sized compressors. Do we have that happening in any condensing units?
Oh yeah, a lot of them.
So we have like a 4-ton and a 6-ton in the condensing unit in order to get 3 stages with 2 compressors. We do that in condensing units also?
Usually in our condensing units, when we do that, when you're talking that small as tonnage, you're in the 38 AUZ, AUD product line. And most of the time, those are equal tonnage, equal split. Okay. So the way you figure out what you have is you go into the product data, and you can look at your compressor model number and the associated tonnage with it. But most of the time on the small units like that, it's equal split.
Okay. Also on compressors, right now we don't have any variable speed compressors on commercial size condensing units. I'm assuming that's true.
Not yet.
Right. So, but we have them residential, we have them chillers, we have them rooftops in a few weeks here. Right. We don't have them on condensing units at the present time. Digital scroll is the alternative on the condensing unit side for the present time.
Yep. No, it won't be long though.
Well, it's the last thing, right? If we got rooftops, chillers, and residential with inverters, we're probably going to educate a guess that the split systems will have them too.
Right.
Juma asks, this is flashing back a little bit. If you already have pipes underground that are buried and oil-filled suction, what can you do to rectify that? Is there anything you can do to try to salvage that?
Yeah, find a different pipe route. You just can't bury them. You can't do it. The only thing and it's not even, we don't even put it in the manual. The only thing that you can do would be like a concrete trench, if you will, and then put steel grates over the top so the pipe is exposed to the the ambient temperatures outside. But you just can't bury the pipe. If you got a job with buried pipe, you need to find another route. No, there's no exceptions to it.
Yeah, especially if in this case, if he already has an oil problem, obviously it's going to happen again and again and again. So anything you do to fix it, it's just going to happen again. So.
Yeah, and then that's usually what happens. You have your first compressor failure because of loss of oil and slugging. You know, you're washing the oil out of the compressor and it's storing out in the system. Then you lose that compressor, put a new compressor in, and guess what? That oil's still out in the system. So you start this one up, you lose oil out of it, you go through the same thing, lose that compressor. Now the third compressor, you've got even more oil in the system. It gets worse and worse, and you can tell those jobs because your compressor duration, you know, how long they last, gets shorter and shorter and shorter. And you know, you have to correct the installation. You can't have buried pipe. If it's there, good luck. I would look for a different route.
Yeah, and there's a few people typing in a follow-up question. I don't know if they missed it before. Maybe you can do the 30-second version on what the reason was for not burying the pipe.
For what?
The reason to not bury the pipe.
To not bury the pipe. Well, it's migration. So refrigerant always seeks the coldest location in the off cycle. So if you think about your condensing unit being out in the ambient, could be a 70-degree day. You know, we probably have 70 degrees across the evaporator indoors or more. And so the coldest spot is going to be the refrigerant piping that's underground, which typically ground temperatures are anywhere from 52 to 60 degrees, depending on where you're at. So the refrigerant's going to migrate down to your pipe. And, you know, the liquid line's already obviously solid liquid, but your suction line needs to be vapor. We fill that suction line up with liquid, and now we start the condensing unit up, start the compressor up, and we draw all that liquid back, and it washes the oil off the bearings in the compressor, doing damage. And even worse yet, you can slug it and start breaking pistons, breaking scroll flanks, just destroying the compressor. So that's what it is. It's all about off-cycle refrigerant migration. You know, if the unit would start up and run and you never shut it off, well, then it would survive because, you know, we're always pulling vapor through that suction line. But it's off cycle is where the damage, the potential damage starts occurring.
Yeah. Chuck asks, what about a heated suction accumulator if you have buried piping?
No, nice try, Chuck, but no. The velocity coming back, if that suction line is full, the velocity of liquid refrigerant coming back in the suction line, there's no way that heater is going to make it flash to vapor adequately. It's just, no, can't do it.
What if you wrap the pipe in heat trace tape like we do with obviously it's not efficient and it's stupid to heat the ground with a bunch of electric heat, but
yeah. Well, that would be that's the biggest thing right there. Is the efficiency is horrible, and then how do you control the heat as capacity changes? And it's just I wouldn't suggest that. And how do you service it? Too many ifs.
Yeah. So it sounds like if you're designing a project where you absolutely positively have to bury the lines, you probably should switch the job to a chilled water design and bury the water pipes and have a chiller feeding hydronic coils instead of having a DX system feeding refrigerant coils. And just be
exactly.
Mark asks, why non-free draining on larger evaporator coil sizes?
Just the way the headers collect, the suction headers, some of them are non-free draining. Number of outlets or spigots, suction spigots into the header, just the whole construction of the coil. There are some coils that they're putting so much in there that you end up having to have a higher point suction stub outs, which require the drain line. It's not many. It's maybe 5% of the coils out there come out that way, but I run into them, probably maybe 3-4 times a year. I'll run into a non-free drain.
Juma asks, how can you avoid vibration leaks, specifically in 25+25 TR tandem compressors?
He's probably talking about the discharge T connection where they're headed together. I'm assuming that's what you're talking about. Usually if that's happening, there's another problem. We've got vibration, abnormal vibration coming off of one of the compressors or multiple compressors due to a slugging issue or what have you. So really need to address the source of the vibration, the compressor itself. We had, and this goes back multiple years, I may even be as many as 8 to 10 years ago, on the 30 RB units, we had that joint breaking, but that was resolved by a different connection point. They had just too sharp of an angle on it. It was breaking, but that's been long rectified. So that's not a current issue that we have if everything is normal. So I would say address the vibration, what's going on that's causing that, rather than, doing something with the joint itself.
Claudine asks, how do you manage oil entrainment on scroll during intervals when the scroll is off?
The longest unload period, that's a great question. The longest zero capacity or unload period is like 8 seconds. It's such a short time. On some units we have 10 seconds on other units, but never really anything longer than 10 seconds off time. So it's such a short duration, and then we're back on 100% that it moves the oil along just fine. But great question. It's again, that's why I was trying to spend a lot of time on the digital scroll, that it's running at 100% or nothing. So at 100% we're moving the oil.
Juma asks, and I think he's still talking about the underground piping, replacing the outdoor unit with a VRF condenser to solve the problem. I don't know why that would be.
You can't bury VRF piping either.
Yeah, I think it'd be the same issue.
We don't Carrier, Bryant, Payne, we don't, and I'm telling you, it's all physics, okay? So nobody else is allowing or encouraging the use of buried piping. We're dealing with physics here. We're not dealing with the blue oval or the Bryant crest or the train emblem. This is all physics. Everybody's in the same boat. I've got articles, I've got papers and bulletins from Train, York, Linux. Everybody is in the same boat. If you get that guy out there saying, oh, no, we can do it, we can bury our pipe, he's just trying to get the job, and you won't see him again once you start having problems.
Yeah.
So, again, this is all physics, guys. It's not manufacturing related.
I agree. If a manufacturer's telling you can do it verbally, ask for it in the written manuals or on letterhead or something, and then see if you still get the same answer. Because sometimes
you won't get it.
Right.
I've been down the path. I've dealt with this, my gosh, going on almost 40 years now. So it hasn't changed because physics hasn't changed.
I'm going to pop up one more poll question. Then I'm going to ask Doug one more question. Then we're going to move on. This poll question is a absolute give me. If anybody gets it wrong, I'm going to be very disappointed. When burying refrigerant lines underground, which must be followed? I'm not even going to read the answers to you. One more question for Doug, though, is this is from Chuck, what is the maximum length you can remote a package chiller evaporator?
It's governed by the model number type of chiller. If you're looking at just the scrolls themselves, like your RAPs, RBs, those are right around 75 feet. You get into the XAs, the big screws, we can get a little bit more distance, not much more. But yeah, usually you're, let's say 100 or under. Depends on the model.
Awesome. For you guys that have not been able to answer the question, other people said that switching between full screen and non-full screen mode allows you to click on the answer buttons, so you can pick the correct answer. Which your choices are: both lines must be insulated, do not bury for more than 25 feet, install copper lines inside a PVC tube, or D, never bury the lines at all. And I'm going to go ahead and close that poll because 70-some% of you guys answered. One of you guys answered wrong. I'm going to look later to see who that was so I can figure out if you're messing with me, because I thought Doug beat this one to death. But with that, we are going to move on. Obviously, the correct answer was do not bury the lines.
Right.
All right.
Right. The only place you'll see anything about buried line is some older residential literature that allowed 36 inches of length of pipe, 36 inches of length,
Like go under a
not
sidewalk or
36
something?
inches deep, but 36 inches of length of pipe could be buried, and that's it. And that's an older res literature. You're not going to find anything else that says anything about buried pipe commercially.
Cool. I think we are all caught up on the questions, Doug.
All right, good deal. All right, so we talked about all the different capacity changes, changing in the systems. If we're doing, multiple compressor racks, we're doing two-stage equipment, modulating compressors, capacity change. So the charts that we're going to get into here shortly. So what we do is we go into minimum capacity tables for oil entrainment. And this is all based on the type of refrigerant. So let's say we got a R410A, and let's say we've got a 1 5/8 suction line. Well, an 1 5/8 suction line, you come down to R410, and then we're at a 40-degree evaporator. If you use these charts, we're always going to use 40-degree evaporator in the table. Comfort cooling, we need 3.3 tons minimum available capacity to entrain oil up a 1 5/8 suction riser. Okay, so that's how these work. If you got a 3 1/8 suction riser, you need 17 tons with 410 at a 40-degree evaporator. So these are minimum capacity tables for oil entrainment and suction risers, not the horizontal sections, strictly the vertical riser sections. So these are the tables we look at out of the engineering catalogs. We say, okay, what's our minimum tonnage? What does the condensing unit go down to? What's its minimum tonnage? Remember I said the one will say we went down to a 10-ton scroll compressor when it's running at 100%. So if we had a 10-ton scroll compressor on the A1 circuit, which is your first on, last off, well, we could entrain oil in a 2 1/8 because we only need 6.7 tons to get that oil up the riser. Obviously anything smaller, but then of course this doesn't give you enough capacity. But you can kind of see how the chart works and where it comes from. Okay, so one of the first things we do is we look at minimum capacity of the unit, and then we go into these tables, and then this information then is transferred to the actual pipe selection tables we'll look at shortly here. Okay, so that's where this all comes from. This stuff's already calculated out for us, so we don't have to go back and figure out the Reynolds number of the refrigerant and do all the engineering on it. It's already done. Okay, so when we look at a regular pipe sizing chart, a couple things in our books now. Make sure that you're in the right chart. We have both 60 hertz charts and 50 hertz charts for our Canadian friends and everywhere else that uses 60 or 50 hertz. Okay, so make sure you're in the 60 hertz chart in the good old US. All right. Then you want to make sure you're on the right unit. This is a 38 APD, D signifying dual circuit. If it was an S, that would be single circuit, an APS, and both are in the same install book. Okay, so we're going to say, hey, I got a 38 APD, I'm in my 60 hertz table. Now I got to find my tonnage. Well, I got a 38 APD, let's say I got a 100, so 38 APD 100. All right, so now I know where I need to be this way, but now what is my total linear length of interconnected pipe? Okay, so let's say we've got 100 feet. Okay, so we come over to this, come over to the chart here. We can go here, we can go here. There's 100 feet on both. So let's use this chart. We come down to the 100 ton unit, and you see that both liquid lines on the 100 are going to be 1 1/8. Both suction lines will be 2 5/8. Okay, so there's our pipe sizes. Now we notice that the 2 5/8 is in the shaded box area. Well, the shaded box area indicates we need a double suction riser on this unit. If number one, the condensing unit is above the evaporator, and two, if our riser section is greater than 3 feet. So 3 feet or more, these shaded boxes mean we need to construct a double suction riser. 3 feet or less, we can use a speed riser. In this case, we came up with 2 5/8 for the suction line. If we did a speed riser, we'd drop down 1 nominal pipe size. Okay, so pretty straightforward there. We go down to 2 1/8 for a speed riser in that 3-foot section. Okay, so let's say we've got a 38 APD 30-ton unit. Okay, now if we look at the 30-ton, we go all the way across. We can go all the way out to 200 feet, and the verticals don't affect us. We don't need a double suction riser on any of the 30 tons, or the 27 or the 25. So double suction risers start at roughly 40 ton. And in some cases, you'll have a suction riser, double suction riser required for either the A circuit and not the B, and sometimes just the opposite. So always look at your chart. That's how it works. Get your unit, your tonnage size lined up, figure out what your length of pipe is, and then be aware if you've got the shaded areas, which indicate double suction risers. Okay. Any questions on that so far?
Not at the moment.
Okay. You get out in this area, in the 0 to 25 feet area, it doesn't matter what size it is. Again, you're not going to need double suction risers because our suction velocities are so, they're high enough because we have such a short run that we have enough velocity, feet per second of gas, traveling through the suction and discharge that we don't need double suction risers. Okay, so it's all about velocity. When we start losing our velocity due to longer piping, we lose our velocity due to unloading capabilities. That's where double suction risers come into play in the vertical sections. Again, if the condensing unit is above the evaporator. If the evaporator is above the condensing unit, we never need double suction risers. Okay. Now, we looked at that and we said, hey, we needed in that 100-ton unit, 38 APD, 60 hertz chart, 100. I came out and I needed double suction risers. So here, come out, and you can see on the 100, my A pipe, remember I said ABC? My A pipe is going to be 1 5/8, and my B pipe is going to be 2 1/8. So what does that mean again? Right down here, my smaller pipe A will be the 2 1/8, and then my B pipe, the larger pipe, will be my 2 5/8. And typically your B pipe, most cases real close to or the same size as the C pipe. And remember, your C pipe is your main pipe going back. Then the 3-foot dimension I was talking about right here. Again, if you're 3 foot or less, you can use a speed riser. And again, the speed riser will be 1 nominal pipe size smaller than what your C pipe is. Okay, so pretty simple. So we go to our main chart, plug in our unit size, plug it in with the equivalent or your total linear length. Your total linear length, by the way, already has 50% calculated into it for fittings. So you don't add your fittings into a linear length table, but make sure that your table does say linear length and not equivalent. Okay, show you one of those later. So we plug that in, we find out what we need to do. We got a shaded area, and we turn the page, and we go to the double suction riser chart, and then this is how it's laid out. Okay, any questions on that?
We did have a question. Josh asks, say you had to go up to a total of 10 feet. You can do it in 4 different risers. Can you do a speed riser 4 different times?
Yeah, you could. It'd be ugly, but you could. I would certainly, personally, I think I would look for a different route or see if I couldn't fit a double suction riser in there and be over, get it over and done with. But yeah, you could.
That's all we have for questions right now.
Okay. Think about cost. You know, when you're adding, you know, elbows, think about resistance to flow, adding elbows. So if we did that 4 different times, obviously we're hitting 3 different verticals, right? So, you know, we're throwing more elbows at it. And, you know, if we're doing stuff like that where we're just putting a ton of elbows in because of whatever, you know, obstacles, you name it, doing things like this, then you really need to sit down and look at how many fittings you have and then add those up. And hey, you know what, are we at 50% equivalent length in fittings? So take your fittings and, you know, look at your long line, look at your length, your linear length, 100 feet. Well, if I add up all these fittings, do they total up more than 50 feet? If so, then you can run into problems there. Okay, so this chart, linear length chart, has 50% built into it for fittings. Okay, just make sure you don't go over that 50-foot, I mean, excuse me, make sure you don't go over that 50% number with additional fittings like that. Okay, and again, double riser construction. The smallest pipe will always be the A pipe, larger pipe will be your B pipe. B pipe typically is the same or 1 nominal pipe size less than what C is. Keep your traps as shallow as possible, ideally making those up with a couple of 45s and a 90, a street 90. It's the best way to do it. What I would encourage you not to do is use those preformed traps. Those things are real deep, and just think about like this, is think about a lot of oil storing in there. We want as little oil in there as possible. We want to fill this trap up as quickly as possible at minimum load so we can get on this A pipe right away and start returning the rest of the oil in the evaporator. Okay. So it's all about velocity all the time on your vapor pipe and your vapor lines, meaning both discharge and suction. Keep the velocity up. Even the evaporators come into play. All of our evaporators are DX evaporators. For our split systems, we use 1/2-inch tube in the evaporators. If you're trying to retrofit a 410 unit on an older evaporator, look at the tubes and make sure they're not 5/8. If they're 5/8-inch tubes in the evaporator, guess what? You got to change it. You can't use a 5/8 tube evaporator on the new 410 units. Okay, it's not the gas, it's not the POE oil. It's simply the amount of oil that's in the new hermetic 410 scroll compressors. So make sure you always are using 1/2-inch tube evaporator coils. And again, it's all a velocity thing.
Doug?
Yes.
On that last slide, Jeff asks, how does the A and B pipe have to rise and where would they connect?
How do they have to rise, and what was the last part, Ryan?
And where would they connect?
So you would come off, in this case, let's say we're coming off the evaporator. This is here's one scenario. We come off the evaporator and our condensing unit's above, of course, so we're bringing refrigerant, suction gas back to the condensing unit above. Coming out of the evaporator, if we've got a real, whatever, a tall basement ceiling or something where we're coming off and, you know, we've got 10, 15 feet here, well, then we would put a double suction riser in here if required by the chart. Okay. So this is one place right at the evaporator coil that it would come into play. The other area is, let's say we come out of this double suction riser, we go horizontally over here, and now we go up a 10 or 15 foot chase. Now there's another double suction riser you'd have to construct. Then we go over horizontal and we go up another 20 foot chase. That's a third double suction riser that needs to be constructed until we finally get up to the level of the condensing unit, and then we go horizontal into it. So any place, any riser that has more than 3 foot length, you have to have a double suction riser if, again, pointed out in the piping chart. And again, if you're in the smaller units, short pipe runs, you don't need them. But the longer pipe runs, you get into some of the larger units starting at 40 ton, that's where it's required. And then based on the minimum oil entrainment charts, and that's where you end up having to put them. Hopefully that answers, I think that answers that. Okay. All right, you there, Ryan?
Oh, sorry, I was answering you, and I have my microphone on mute. Yeah, we're all good.
Oh. Okay. All right.
Thank you. You want to
All right.
you want to take a break here for everybody?
Well, yeah, let's finish this because we're done with suction lines if there's no questions. So let's just summarize on this slide here, and absolutely we can take a quick break.
All right, cool.
All right. So remember, in suction line design layout, keep them as short and simple as possible. Least amount of turns and short as possible. You want to design for 2-degree line loss, and again, you don't have to worry about that because this chart's already done that for you. This is already based on a 2-degree equivalent pressure drop. Okay. So, but design the lines for 2-degree. I'll talk about different temperatures later on in some slides. Check for oil return at minimum load conditions. Again, that's already done in the chart. But understand that there is, in fact, a table that does that for us. Okay. Pitch the horizontal runs back towards the compressor or the condensing unit, 1/8 inch per foot. Loop the pipe to prevent drain back. This is the inverted loop at the top of double suction risers, like this and this. Or if you're just coming out of the evaporator coil, going up to the horizontal section, always put that little inverted loop in. Traps, we don't want those intermediate traps, you know, the 10-foot riser traps, any traps, we don't, you know, just, the only time we want traps, excuse me, would be in the construction of a double suction riser. So no traps anywhere else outside of the inverted traps. Okay. Of course, suction lines need to be insulated. Isolation valves for the compressor. Those are always nice to have. A lot of times those are already built into the unit. Filter dryers should have isolation valves if they're changeable core style. Gauge ports, I wouldn't put gauge ports in. Most of our equipment, can't think of too many already have gauge ports, so really no need to put additional gauge ports into the suction and liquid lines that are field installed. And suction accumulators, again, we'll let you know, or if you have questions, call us, but you know, use those sparingly and only where needed. And again, if there's any questions, give us a call and tech support, commercial lines, and we'll help you through that one. So with that, Ryan, we'll take what do you want to take, a 5-minute break?
Yeah, let's do that. One question on the suction before we go. Should suction accumulators be insulated, Grace asked.
You don't have to insulate them. You could, but you know, they don't have to be insulated. You know, the accumulators are mounted right at the unit itself, at the condensing unit itself, or the chiller itself. So typically at the accumulator into the compressors, they're not insulated.
Okay. It is 10:34. Let's just come back at 10:40 even. So if anybody needs to go hit the restroom, double down on coffee, all that stuff, we'll resume promptly at 10:40.
All right, sounds good.
All right, cool. While we're waiting for everybody to jump back in, I'm going to go ahead and launch the next poll question here, just so we have it going. But we'll leave it open until, an extra minute so everybody can get back. In row split applications, which is proper? Inlet side of the coil must be first on, last off. Discharge side of the coil must be first on and last off. Top coil, first on, last off. Bottom coil, first on, last off. And once again, if you're having trouble clicking on it, change between full screen and regular screen, and you should be able to click on the options. And I'll leave them up here for a minute. While we're doing that, since it's 10 seconds before we start, I'm going to go ahead and ask a question that came in on the break from Chun. He asked if the liquid line should be insulated, Doug.
No, we don't insulate liquid lines on our commercial equipment. Now, you want to be careful on some of the duct-free split systems because their liquid line actually isn't even a liquid line. It's a multi-phase or tri-phase line. But with standard DX commercial, no, we don't insulate the liquid line. With one caveat to that. If by chance you're running through a real hot attic or space, at say 100 degrees or higher, then it would be worth insulating it so we don't end up with flash gas in the liquid line. But as standard on a normal installation, no, you don't have to.
Awesome. Anybody else have any other questions for Doug on anything we covered the first hour and a half before I close this last poll question? We move on. All right, I'm going to close this question in 10 seconds. I'm giving you a warning because only 58% of you picked an answer, and half people got it wrong, so apparently it's a tricky one anyway. Or I worded it poorly, one of the two. All right, I'm going to close it. The correct answer was, in fact, B, which would be the discharge side of the coil in a row split application needs to be the first section on and the last section back off. I think we are all caught up on questions, Doug.
All right. And if we'll look at the time at the end here, and if we have time, I'll run back to those coils since there's a lot of interest in that.
Yeah.
Moving on to the discharge line.
Oh, sorry, go ahead. I was saying, to show you the results, only 41% of people got it right. So I think they didn't read the row split and they thought it said face split or who knows what. But maybe we would review it. Okay, thanks.
We'll go back and review it in a bit. All right. So moving on to the discharge line, another vapor line. So discharge line sizing and the effects of it. If we undersize, again, it's going to reduce system capacity. It'll create higher discharge pressure, higher compression ratio, which is a really tough one on the compressors. Reduced efficiency. If you oversize it, just like on a suction line, you're not going to entrain the oil. Your velocities, your gas velocities go down, and you just simply don't entrain the oil and bring it back to the compressor. It sits out there in traps and low spots. So, and low oil levels back to the compressor, obviously that's self-explanatory. So these new compressors, and I say new, they're not new, but these scroll compressors, the hermetic style compressors, they don't have the volume of oil that the old semi-hermetics used to. The old semi-hermetics used to have anywhere from a gallon to a gallon and a half of oil in it, and then some. Nowadays, we don't even have a gallon in these hermetic compressors. So we need to get as much back as quickly as possible. And that's why these line sizes are just so critical on these units. There we go. So discharge line sizing is basically, it's the same thing as almost sizing the suction lines. It's all the same practice. First, we need to figure out what the distance is. In this case, we got a foot off the compressor. We drop down 3 feet, over a foot, up 14, over 2. We get the total linear length, okay? Now, this is a little different here. Now, this is what was called a commercial triple split. What we don't see is the evaporator over here, but we had just a compressor unit. Typically, it was in the basement, and we did come out and we did do a regular trap on these years ago. We didn't want to come out and go straight up because we didn't want that any kind of refrigerant or I should say any oil coming back and sitting on top of the head and waiting for the compressor to start. So we always came out and went down and then went up, and we also had a check valve in them. Okay, but this is just for pipe sizing here to kind of illustrate the pipe length. So we want to get our total pipe length needed for the calculation, just like before. We need to know if the condensing unit, in this case a condenser, is above or below the compression unit, the compressor or what have you. Now, these are a little different when we're sizing discharge lines because we no longer have a condensing unit. We have a condenser that is compressorless, right? Because the compressor's down here, or the chiller. So a couple things on this with the piping. When we're doing discharge piping and the condenser is above, we always want to take the discharge pipe and come up equal to or higher than the actual condenser coil itself. Now, on the carrier condensers, when we get below 60 ton, this, we'll call it inverted trap, is already constructed inside of the unit. So we can come up and go right into the liquid and hot gas, or liquid and discharge gas stub outs, okay? But on the larger units, we don't have that internal trap made, so you're going to have to take the field piping and come up equal to or slightly above the condenser coil, okay? So that's a little different there. Now, this is where we can also get into a double discharge riser. It's constructed the same as the suction double discharge. I mean, the double suction riser. It does the same exact thing, and we'll get into some slides here and show that. The discharge, because it's a vapor carrying pipe, we can get into oil entrainment problems when our capacity is way down on our compressor or condensing unit or chiller, okay? So this is what we're going to look at now, is just hot gas. Here's a good picture of this inverted loop up at the condensing unit, and this is again on larger sizes like 60 ton above 60 ton. You need to form this. Below that, again, this inverted loop is formed in the inside of the machine, so you don't have to do that. So always beware of what unit you have. Look at the installation book. It will tell you if there's an inverted hot gas line trap in it already or not. Okay, so always be conscious of that. So a couple other things on these. There's many applications, especially our screw chillers, like our 30HXs and XAs, things like that, especially if we're doing any kind of remote stuff. We need discharge line check valves in them. Okay, so a lot of things to think about here, and all covered in the install manual. So if you're not familiar with the product, whatever product it is, always take time to review it. There is so much in the installation books, and we're really good, Carrier's really good at putting some of the most important detail in the smallest font print in the little notes below the various figures and pictures in the book. So, you know, when you call us for help and information on stuff like this and piping, you know, this isn't stuff we're just kind of pulling off the top of our heads. We're always resorting to the install troubleshooting books and, you know, some of the other material we have. But basically, there isn't any reason why we couldn't go out to any of our chillers, condensers, condensing units, and go through the book and find everything you need to properly install it when it comes to the piping side. So it's all in there, kind of scattered about, but it is in the book. So, but, Yes.
While we're on this drawing, Mark has a really good question. For City of Chicago code, where exactly do the relief valves get installed to satisfy the city?
The relief valves, so the whole purpose of the pressure Chicago code valves, we call them nowadays, pressure relief valves, they always go in the liquid line. The reason we go in the liquid line is that's the fastest way we can evacuate the charge out of the unit, blow it out into the atmosphere in the event of a high pressure scenario or a fire, right? That's what they're for. So they should always be in the liquid line, and in this case, somewhere out here near the unit, because we want to be outdoors. Now, depending on what the total charge is, sometimes we have to pipe these relief valves to some type of manual, or not the relief valves itself, but we got to pipe the liquid lines to some type of manual dump valve, fireman's dump valve they can get to. Basically, in the liquid line, and I would always put it at the outdoor section, because that's ultimately where we want to get the gas. And the liquid line is going to, again, relieve all the pressure the quickest. So hopefully that answers the question. Okay. So in sizing these liquid and discharge lines, it's just as simple as going into the sizing for the suction pipe. We need to look at what unit we have. In this case, I'm grabbing a 30HXA chiller. And let's go down to a 146 size. And we look at the 146 size, we come across, there's our A circuit and our B circuit. Okay, here's our pipe sizes, and here's our distances. So 0 to 50 feet right here. Come to my A and B. My liquid line should be 1 3/8, 2 5/8 on the A circuit, and 2 1/8 on the B circuit. So always look at your discharge lines and your suction lines in these charts, because these can change, and so could the liquid line size. You look down here, here's a 2 1/8 and 1 3/8 liquid line size. They can change because the A circuit and the B circuit capacity isn't always a true 50-50 split on some of the units. Some have larger A circuits, some have larger B circuits. So it's real easy, especially with my old eyes, to come in here and say, oh, they're both 2 5/8. Well, no, they're not. That one's 2 1/8, right? So look closely at these charts. The other thing you want to do is look at all of our notes. Remember what I said before, we're really good at hiding pertinent information, important stuff, and all of our little notes, footnotes. So, here we've got an asterisk, here we've got a cross. Well, what the heck does that mean? Well, you're not going to be able to tell because I cut that off, but I'll tell you what it means. If you see the cross on the discharge line, guess what? That means you need a double discharge line if the condenser is above the chiller, and if you have minimum load valve on it. So the HXAs are screw compressor chillers that have a minimum load valve on it. What's a minimum load valve? Well, think a hot gas bypass with a new name. That's what it is. So if you have the minimum load on these chillers and the condenser is above, and like a suction line, if the vertical section is longer than 3 feet, we need to do a double discharge riser. Okay, so always look at our little notes, our little asterisks, our crosses, there's X's, we have all kinds of stuff in there. So, or just simply numbers like 1 through 10. So always see what the note says, and always note that in this case on the HXAs. So, but again, pipe sizing is as simple as figuring out what model number you have, what your total interconnected pipe length is, linear length, and it will give you your feet, or your meters, how many meters. We have both. If anyone's wondering what that number is, well, that's your SI numbers. So, but again, that's simple. Model number, A circuit, B circuit, how long, there's your pipe sizes, okay? Always look for little notes, asterisks, crosses. Doug? Go ahead.
Larry is asked, what book do you keep referring to? You've mentioned a book a few times. He's asking what book that is.
The installation manuals. So this is just a cut and paste out of the install book, out of the 30HXA. If you're looking for specifics, it's a 30HXA SI20 book.
Yeah.
That's just
all of our carrier books for every piece of equipment. There's tons of literature for each thing, but there's two books that you look at a lot. One was what we call product data, and it's kind of like more at the design side of the equation, basic product function, sizing, capacity, HRI ratings, all that kind of stuff. And then we have the install book. And some stuff's in both books because it applies to both the installer and the designer. But it looks like to me, and probably to Doug as well, that you always need both books to do anything.
Yeah, you do. There's,
put it all in one book.
Your control information, everything like that is in the control troubleshooting books. Your piping, duct connections on rooftops, all that stuff's always in the install book. And you should be able to see my screen no matter where I go, right, Ryan?
Go somewhere else and I'll answer you.
You can see that, right?
Yeah, you can see you went to your slide deck.
You can see that, right?
Yeah, so you're good. Wherever you open from there, we'll see it. Unless you have two monitors, we can always see what you see.
Yeah, so this is just a folder I have with all the various books in here. And we have things like, let's see, like over here, a 30HX14SI. Let's grab that. And that's an install book for the chiller. You know, and in here, we'll talk about all kinds of things. You know, this is where your pipe charts are at. That's where I got that stuff. It's just all cut and paste out of these books that I put this presentation together with. We have PD books, which are product data books. It gives you all the different specs on the machine. We have T books, which are troubleshooting books. The T stands for troubleshooting. So all these books come with the machine. So you can see control, startup, operation, troubleshooting. Go down to the bottom, you can see it's a 30RB7T book. So that's what that's all about. SI is startup and installation. T stands for troubleshooting, and PD is product data. So, and you can see that, you know, this is where I go to all the time. This is my whole library of, you know, all kinds of different stuff, information, and all the catalogs and books.
And you can see Doug downloads them on his computer because he's answering questions all the time, nonstop on this stuff. Other people like myself and most of you guys, you don't need to download millions of books. Just go find them on demand as you need them. And they're on multiple websites, but probably the best, cleanest place to find all the carrier literature that you need for most things is carrier.hvacpartners.com. I'll throw that in the chat group as well. But if you go to that section, you can pretty much find any current stuff in terms of manuals, sorted by equipment type. If you have any problem finding stuff, let me or Doug know, and we'll help you hunt down whatever you're trying to hunt down. There's like 100,000 documents on that site, literally over 100,000. So it's a lot.
All right. Just know that you have to have an account to get in it, though, to get into the server. So some of the stuff you may not be able to grab if you don't have an account number.
Right. So the new one, carrier.hvacpartners.com, you can access things publicly on that one now. You don't have to log in like the old hvacpartners.com.
Yeah, but there's a lot of troubleshooting that's missing out of that.
Indeed.
A lot of the important troubleshooting books are gone. They're not in there unless you've got an account. So, but anyway, if you need that, if it didn't come with it, you can give us a call too, and we can email it to you as well. So, like I say, it's just at a finger touch to grab any of these books and email them out to you. So, but all right, let's get back to this. But pipe sizing again, in this case, we have a screw chiller, just very simple, model number, length of pipe, line it up, and there you go. Here's a different chiller. Here's a 30 MPa chiller that also uses a air-cooled condenser. Same thing, model number, what tonnage, let's grab an 045, 0 to 50 feet. Guess what, I'm shaded in here. That means I need a double discharge riser if the unit is equipped with a hot gas bypass control on it, or again, minimum load valve. MLV is essentially a hot gas bypass. We just changed the name and made it sound new, but it's the same thing. We're injecting hot gas, which we'll look at in a few slides here. But same thing, distance, boom, boom, boom. That's simple. Okay, so that's your main piping. Now, if you need double discharge risers, and like in the case of this chart, we'll go back here, and I said, okay, hey, got the T on here, go down to the note. If I got minimum load valve, I need double discharge riser if the condenser is above. All again, again, based on a minimum tonnage for oil entrainment in a hot gas riser. Remember I showed you the one for minimum tonnage for oil entrainment in a suction riser. This is for a hot gas riser. It works the same way. 410, 40-degree evaporator, inch and 5/8 pipe. Come down here. I need a minimum of 10.23 tons in order to entrain the oil up a hot gas riser. Okay. Now, this machine is going to get down to some lower tonnages because we've got hot gas bypass or minimum load control on it. Okay. So at that point, if we find out we need a hot gas riser, and again, the 3-foot rule is in place. If I'm more than 3 feet, then I need it. If I'm less than 3 feet, I can use a speed riser. Okay, same thing. And of course, there is a chart in the book for your double suction risers. Now in the 30HXA manual, a lot of people kind of stumble on this one a little bit. Again, model number 30HXA, what size? Let's say I got a 146. The 146 is coupled with these two condensing units. I've got the 09DK 084 on the A circuit. I got an AZV 142 on the B circuit. I look here, and here's what people get caught up on this. It's like, okay, how do you read this? And simple as it seems, it's easy to overlook. This is always your A pipe. So this is your A pipe dimension. And from here over, depending on length, is your B pipe dimension. So your A pipe dimension is going to carry you from 0 to 200 feet, but your B pipe, we need to look at, you know, are you 0 to 50, 50 to 100, 100 to 200. And again, A pipe, B pipe. So A pipe is going to be basically your speed riser pipe when the trap is full of oil because you're at minimum load. So minimum load, we're not returning oil properly, or not pushing oil, I should say, properly. So we fill the trap up, and now our velocity picks up in the A pipe, and boom, now we're entraining oil back up to the condenser, out to the evaporator, and then back to the compressor. Okay. So that's how this chart reads. So again, any of the carrier charts, they're pretty detailed. You know, and they do a great job. They're accurate charts. You just have to get used to them. Everybody does something different. Train does a little, you know, there's a little different. York, Linux, you name it. Everybody's a little bit different. But at the end of the day, it's all physics, and the dimensions are the same. It's just how you navigate the charts that are different. And carrier, we put a ton of information in our books, tons of little footnotes down at the bottom of every chart. And then there's little idiosyncrasies about it, just like this. You know, riser A is in this column, and your B riser is over here, based on different lengths. Okay. So, any questions on discharge pipe?
Don't see it at the moment, but I'm going to launch one of these quiz questions while people think about asking you a question.
Yep.
So this one, where should City of Chicago or other pressure release valves be installed? Your choices are going to be suction line outdoor, suction line indoor, liquid line outdoor, liquid line indoor. Two of these should be pretty easy to mentally eliminate.
Now let's be a little, before you do that, Brian, be a little careful with that liquid line indoor, because the relief valves, like on the 30HX chillers, be it a HXA air cooled or a HXC water cooled, they do have the reliefs indoor at the chiller, and you have to pipe the reliefs to the outdoor.
I guess that gave you all the answer. So now we're good.
All right.
you don't have the answer now, then I don't know what to tell you guys.
Yeah. See how that worked?
Got to have a few gimmies in here.
Mm-hmm.
Wait till you see the last question. If you get that one wrong. I don't see anybody else typing any questions in for Doug to answer. So I'm going to give this 10 seconds and I'm going to close this poll and we're going to move on.
Okay. Well, we're moving along good. So be right on time or earlier.
All right. So you guys that have not answered, I'm closing it now.
All right. Discharge line, going over this a summary of it again. Just like the suction line, you want to keep it as short and simple as possible. Short as simple keeps your velocity up. With the velocity up and the vapor, better oil entrainment. And just always remember that the vapor state of the gas, it has a little bit harder time in training the oil. There's just not as many molecules of a refrigerant, if you will, to adhere to the oil and then train and bring it back. Okay, so vapor is always your challenge. Liquid line, that's got no problem bringing oil back at all. So, all right, so short and simple. All right, 2 degree design. That's standard again. You know, look at oil return at minimum load. Fortunately, nowadays that's all done for you in these charts. But just know that there are entrainment tables out there. Horizontal pipe, make sure it's pitched 1/8 inch per foot, again in the direction of flow, all right, which is going to be back to your condenser. Inverted traps at the condenser. Remember that you get up around 60 ton and above, the inverted traps are not in the condensing unit, but below 60 ton, they do have already inverted traps constructed inside the condensing unit, at least on the carriers. Now, I can't vouch for anyone else's equipment. Always check with the manufacturer. So, then isolation valves, you know, hey, I'm a service guy, so I love isolation valves. You know, I like the isolation bypass valve around filter dryers. I like isolation valves at the condensing units, the condensers, the chillers, which many of our pieces of equipment already have those standard. But always think about that, you know, for service down the road. Okay. Hot gas bypass or minimum load valve, pretty much the same thing. Hot gas bypass, we actually have a hot gas bypass run. Now this is typically on split system condensing units. And we'll take off the hot gas line and we'll take hot gas and we'll bring it down through a regulator valve and a solenoid and inject it right at the evaporator to bring the evaporator pressure and temperature back up, you know, into normal ranges, so we don't lose superheat control, we don't, you know, flood back, we don't have other issues, just kind of a capacity control thing so we can keep the system online. We're not frosting or freezing evaporator coils, all that kind of stuff. So it's an older, completely inefficient way of capacity control or maintaining an operating envelope of pressures that's suitable to keep the evaporator clear of frost and compressor happy. Oil return, you know, with the increased pressure and temperature, we're increasing the velocity through the evaporator and this suction, multiple uses for it at low load. So if you've got a compressor or a system that can unload, you know, way down to, you know, 10% or 33% or less, whatever. And sometimes we want to look at some type of minimum load, false load device. So there are there's raw valves out there. They do things a little different, but basically it's hot gas bypass, if you will. When you get into this style of hot gas where it's truly piped, you do have to size a hot gas bypass line. You go to a regular hot gas bypass sizing chart, or excuse me, hot gas bypass line sizing chart, which is basically a discharge gas chart. And most of these valves, hot gas bypass valves, are somewhere between 2 and 7 tons of capacity they can offer to the system. So basically you size the pipe off the tonnage of the valve. If you got a 7-ton capacity hot gas bypass valve, then you size this pipe for 7 tons, which usually are around 5/8 or 7/8, somewhere around there. So that's how that all works. Basically what it does is hot gas line off the compressor before you hit the condenser. You got a solenoid valve, typically, that's going to be controlled off some type of capacity control. Then you have the hot gas bypass valve regulator that's adjustable. So at what pressure do you start regulating hot gas into the evaporator section? Well, if you have this older style, where you inject is a special ported T. Okay, so normally your distributor, so if you look right here, this is your distributor, you typically would have your TXV connected right to it. So TXV ending right here, that would actually go on right here. Well, to put hot gas bypass on, the TXV comes off the distributor, or you hadn't put it on yet, you install this ported T, and then the TXV installs onto the port. So another picture right here is a little bit better. So picture again your distributor right here, your distributor tubes. That's this area right here. Now your distributors, as they come with the coil, with the evaporator coil, they're going to have a nozzle in it. It's located right here in the distributor. We'll talk a little bit about nozzles in a second. So if you're going to do hot gas bypass, you have to add on this ported T. Sporlin is the manufacturers of them. You take the nozzle out of the distributor, you put the T on, and now you reinstall the nozzle at the inlet of this ported T, and then your TXV fits on over here. Okay, so the side connect T, ported T, goes in between your TXV and the distributor of your coil. And then when your hot gas solenoid valve's energized, and if the regulator sees that you are at whatever pressure, well, back to this, if we looked at R22, we usually set these regulators to start allowing hot gas flow in at 57 pounds gauge suction. And on R410, we're upwards of around 100, 108 PSI gauge suction, where we start regulating hot gas in. So just kind of a method of capacity control, and really at the end of the day, what it's doing is maintaining pressure and temperature in your evaporator, so we get proper oil entrainment, we have proper pressures to keep us again above freezing or frosting of the coil. So it's kind of how this thing all works. So hot gas bypass, that's another pipe you may have to size on a job. And again, if you're on the job, give me drawings of where everything's at, and we'll get it sized up for you. If you have multiple coils, going back to this slide now, if you have multiple coils, the hot gas bypass always goes on that first on, last off coil. And this is probably a good slide here to go back to that question. When we look at the coils here, okay, we have two individual coils that are stacked on top of each other, okay? If we look at this as a phase split application, then we would literally cut the coils right here and call this our first circuit, or first stage, and call this our second stage, okay? So the bottom coil would always be first on and last off. So in a sequence of operation, the lower coil, that circuit would come on, then a Y2 call or second stage call comes in, the upper coil comes on, now we're running 100%, now Y2 or second stage is satisfied, this coil shuts off, this coil is still operating until it shuts down, okay? Now in a row split, which goes back to that question, a row split coil, we take each coil and we divide it down this way, okay? So we have a circuit on this side of the coil, a circuit on that side of the coil, circuit on this side of the coil, a circuit on that side of the coil. In this case, we need to look at our first on circuit being on the leaving air side of the coil, okay? And then our second circuit would be on the entering side of the coil, assuming the airflow is traveling this direction, okay? Airflow is going that direction. So again, first on, last off, first on, last off. Now, in the case of this piping, if we look at the piping, we're piped in a full face application, okay? So our suctions are returning one common suction, both coils. We have one common liquid line feeding both coils, but we could get into a condition where we have a second solenoid valve that's controlling our second stage, okay? So again, leaving side of the coil would be first on, and then second stage would bring the entering side of the coil on. Second stage satisfies, the entering side of the coil is shut down, leaving side of the coil still energized until we're satisfied with a complete call for cooling, okay? So hopefully that clears up the row split issue on the coil, and then the phase split as far as control goes. And then remember, there's also what's called the intertwined coil, and there is no row split. So it doesn't matter if you'll have two circuits, but it doesn't matter what circuit you're on. There is no entering, leaving side of the coil circuit. They're intertwined, so each circuit covers the full area of the fins. Okay, and that's, like I said before, that's 90–95% of all coils we sell are intertwined style. Now you may have a couple of intertwined coils where we have to deal with the phase split issue, because remember, we always want full phase typically in any DX cooling application, especially in VAV and VVT applications where varying airflows and things like that. And the reason behind that is a VAV unit is always going to control to a discharge temperature, okay? So if only the bottom coil is active and running, and this is our discharge air over here, and let's say we're trying to maintain 55 degrees supply air temperature, discharge air temperature, and we only have the lower coil on, we're never going to get there because of all the dilution air coming through the inactive coil. And we can actually drive our suction down really low on this coil trying to get to that 55 degrees, which we'll never get there again because of the dilution air from the inactive coil. And the unit runs and runs and runs. We start really dropping the suction down. We could start freezing, frosting. We could start flooding back, all kinds of problems. So again, VAV, VVT never have phase split. Again, typically phase split is more of a process application than a comfort cooling type application, okay? So hopefully that cleared that up a bit.
Yep. Could we ask a few questions while we're at a breather here?
Sure.
Chun asks, for double riser, do both risers need an inverted trap?
Now we'll use, tell you what, we'll use this one. So when you're constructing either a hot gas riser, or let's say this is a double suction riser, when you come up, yes, the B pipe should go up and down into the main, and your A pipe should also come up and have a little inverted trap here. I think I had maybe a better picture somewhere showing this. Right here. So yes, you should have an inverted trap at the top of a double suction riser or a double discharge riser.
Awesome.
Hopefully that covers that.
Lance asked, when you refer to oil, are you referring to the liquid refrigerant?
No, when I'm referring to oil, I'm referring to the compressor oil, like POE with 410 or mineral with R22. I'm talking literally the compressor oil. Any time a refrigeration circuit is running, if you're doing comfort cooling or whatever, we're always carrying a little bit of oil with the refrigerant out of the compressor. So the oil is being entrained with a discharge gas into the condenser. That oil is traveling all through the liquid line, through your TXV. It's not a lot of oil, but it's a little bit of oil. through your evaporator, and then we're returning that oil back to the crankcase through the suction line. Well, as we return oil, we're also taking additional oil out through the discharge gas. So the refrigerant vapor can always entrain the oil, and of course the liquid can too. It's just the vapor state lines have a little bit harder time at entraining oil, so it's a slower entrainment that occurs, unless of course we flood back. If we're bringing liquid back, so something's wrong with the system or metering device or what have you, low load, we start bringing liquid back. Liquid is really good at entraining. Its miscibility with oil is fantastic, and it just washes all the oil out of the compressor and carries it out. And then if your pipes aren't sized right, or you got some issue going on, then we can't get that oil back to the compressor. And then what people do is, oh, I'm low on oil, they add more oil. Well, then that oil leaves, and it just is this endless circle that ends up in disaster by compressor failure. So no, when I say oil, I am talking about oil, compressor oil.
Yeah, I've found over the years a lot of people realize there's oil in the compressor. There's mechanical parts grinding together, but they don't realize that the oil is entrained with the refrigerant. They don't necessarily get that until they have a problem job the first time. And then they're like, oh yeah.
Right.
Installers realize it, but on the design side, we don't always realize.
Right. And some compressors have oil in them, meaning like an oil sump. Right. So all of your hermetic scroll compressors will have an oil sump and a volume of oil in it, varying, from multiple ounces, 64 ounces or less. Semi-hermetic compressors, reciprocating, have an oil sump in them. But now we get into the screw compressors, and your screw compressors do not have oil sitting in the compressors. We have an oil separator, an oil vessel in the system that manages the oil that's pushed around by two things. One, an oil pump, just like in a car engine. And then two, the differential of suction and discharge pressure keep the oil in circulation on our screw compressor chillers. And basically we have oil ports through the compressor that lubricate the bearings and the lobes of the screws. So not all compressors have oil that sits in them, but all refrigeration systems have the oil moving through it via entrainment with the refrigerant.
Awesome. The only other question was from Juma, who asked about hot gas bypass, but I think the question was typed in right before we went into this section, so I'm assuming we answered all of it. If not, Juma, let us know and we'll ask the questions again. I think we're caught up on questions, Doug.
All right. So let's talk about the liquid line a little bit. Liquid line designs, typically they have the same routing as the suction lines. Things we have to watch out for on liquid lines, and they're certainly way more forgiving, liquid lines are. Okay, so they have no problem in training the oil. Our velocities aren't as big an issue, but you can get into trouble with oversizing. You got to be conscious of liquid lift. What liquid lift is, when we talk about pipe design, it's literally just what it says. It's lifting the liquid refrigerant uphill. Okay, so if our condensing unit or condenser is below, that's different than if it's above. If we have a condensing unit below and we're trying to push liquid uphill to the evaporator section, well, that column of liquid that's going up vertically has a specific weight to it. So now not only do you have the friction loss of the pipe working against you, you also got the weight of the refrigerant and that liquid vertical column of liquid. So what you'll find is in condensing unit manuals, you will find liquid lift tables, and it will tell you how high you can go with the various tonnage, various model units. So one model may say it's got a liquid lift capability of 56 feet, the next one may be 80 feet, and it just goes by tonnage. So remember, a ton of refrigeration is pretty much equivalent to 1 horsepower, at least when we're dealing with 410 and 22 and 134 with the standard comfort type applications. So that liquid, you know, anytime we're lifting a weight up, it requires horsepower. So the more liquid you have, the more weight, the more horsepower it requires. So we limit the height because we go beyond those limits, and now we're losing so much horsepower, we're losing capacity. So we say, hey, here's a 50-ton condenser, and you can go 200 feet uphill. Well, yeah, but the problem is now you've got maybe a 20 horse or 20-ton system. You don't have a 50-ton system anymore because you used up all the horsepower trying to push the liquid uphill. Okay, so think about all those things with liquid lift. There is a limit on how high you can pump the liquid refrigerant, and that goes even with the little residential stuff. So same thing. Now, of course, pumping liquid downhill is no problem because gravity is on your side and works, right? But you also have to watch going downhill because that same column of liquid can cause metering devices to overfeed. Okay, because not only do we have the pressure from the compression cycle, we've also got the weight. So always look for liquid lifts and see if there are any vertical separation limits if the evaporator is below. Okay, so liquid line design, we always want to be careful with liquid lifts, see what your limit is. We also need to be careful about oversizing liquid lines. And what happens if you oversize a liquid line, now we start getting into that too much liquid refrigerant in the system, or too much refrigerant period in the system, and we get into what we call a refrigerant management issue. And that takes us back to that simple rule of thumb formula, no more than 4 pounds of refrigerant per ton of refrigeration effect. Okay, so if I got a 10-ton unit again, I got a 10-ton unit, that 10-ton unit system can't have more than 40 pounds of refrigerant. Okay, so how is that calculated? Well, we have charts that tell us how many pounds of refrigerant are in 1 foot of liquid line, depending on what size liquid line it is. So, you know, you could have 2 pounds of refrigerant per foot. You go down to little 3/8 pipe, you got 0.6 ounces per foot, and that's all got to be, you know, it's all got to be accommodated for. And we want to make sure that, you know, if we have long lines or oversized liquid lines, that it doesn't equate to more than the 4 pound per ton number. So those are the risk of oversizing liquid lines. Undersizing liquid lines, you know, although I say right here, smallest line is better, but undersize can reduce capacity on you too. So be careful with undersizing. And it's simple to do. Just stay by what the chart tells you to use. Go on the chart, here's your liquid line size, here's your suction line size, or your discharge line size. Do what the book says. It's all been tested and rated, and we know it's accurate. So sizing, and we'll look at some charts, and really we can look at any of the charts we were looking at. Your liquid line sizing charts are this simple. It's right there. You go into the chart, it's right here for this chiller. You know, you go into the MPs, you know, here's your liquid line. If I went all the way back on the slide tray, back to the suction, on those charts, you've got liquid lines. So sizing's simple on liquid line. You just go to the chart. We don't really have any kind of an entrainment chart for a liquid line because there's just no problem in training oil in the liquid line. So, but some of the other things to think about, capacity control via solenoid valves. You know, sight glasses are nice, filter dryers. You know, how are you going to arrange all this for capacity control? In this case, when the unit's not running, this liquid line will be closed, or liquid line solenoid valve will be closed, so will this one. If stage 1 or Y1 circuit starts up, that's going to open up. Here you're feeding the bottom coil like we should be. Y2, second stage comes in, that'll open up. Now we're feeding the upper coil. So, you know, your refrigerant specialties, which we consider all these things your refrigeration specialties, including accumulators. Those all have to be laid out properly. And again, our installation books will do that for you. They'll give you the layout and suggested methods for controlling multiple coils. So that's all in there as well. Now, the sight glasses here, when we put them in, that's great. That will tell us if we've got a solid column of liquid at the TXV, which we always want. We don't want flash gas through here, which you still could have on minimum loads once in a while. But sight glass charging is not for the new equipment. All the new equipment, really, you're best off charging by weight. At least for the absolute minimal charge, which I've got some slides coming up on we'll look at. But just like residential, a residential condensing unit comes with a weighed-in charge in it from the factory that is enough refrigerant to work on a system with 15 feet of interconnected liquid line. Okay. Commercially, these numbers are found in the product data book that I showed you. The product data book will say this particular tonnage unit requires this much refrigerant for 25 feet of liquid piping. Okay. So to calculate a weigh-in charge, we just simply figure out how much additional liquid pipe we have over the 25 feet. We look at the chart to see how much refrigerant is contained in whatever diameter liquid pipe you have, be it 1/2 inch, 5/8, 7/8, all the way up to 2 5/8. And you calculate that together for your total length of pipe. And from there, then, of course, we have to accommodate for the evaporator. The evaporator, especially in commercial equipment, it's got some appreciable amount of refrigerant in it. And between all that, you calculate out a total charge, weigh-in charge, and you may have to trim it by 1/2 pound or pound, but if you measure accurately and your math is accurate, you can get, like I say, within 1/2 pound to a pound of charge by weigh-in method. And that's what we recommend nowadays. Most all the equipment, especially chillers, they're oversized nowadays. This is plain and simple fact. They're oversized, and some grossly. So you're never going to get that machine to get to a full load state, not even at 95 degrees in many cases, to charge by chart. So in full load state on commercial equipment means all compressors are running. They're all running at 100%. All condenser fans are running and at 100%. In the event you've got motor master, and then your coils need to be full active. And to get to that state with load alone, with the oversizing that's out there, is just, it may be 1 or 2 out of 10 that you can actually do it. But so understand weigh-in charge. It's the way to go, and that's how it's calculated. Again, you don't calculate for your suction line, you don't calculate for your discharge line, you calculate for the liquid line, the evaporator coil, and what the condensing unit or chiller's operating charge is for 25 feet. Add it all together, and that's your best starting point.
Hey, Doug, we've accumulated a lot of questions on this section. I read a few of them to you here?
Yeah.
All right, so Mark asks, regarding oil in the compressors, scrolls versus screws, does the oil storage in a scroll compressor make it less sensitive to oil issues compared to the screws?
No, it's a different animal. So the scroll compression compressors, those are in our split system condensing units, typically, and in our smaller chillers. And they have an oil charge in them, but it's a small oil charge. In some cases, less than 64 ounces oil charge. So there's not a lot of available oil there to be out in circulation, and that's why we have to eliminate traps. You can't have traps everywhere, lift station traps, and the only trap again, true trap like a J or a P trap, a J trap, is in a double suction riser or a double discharge riser. Outside of that, you shouldn't have any other traps in the unit, with the exception of the inverted trap at condensers, but inverted traps don't store oil. But so those are sensitive. You get into screw compression, like on our chillers, for instance, like the 30HXs, you know, HXA, HXCs, those are going to have anywhere from 5 to 7 gallons per circuit in them. But if you've got long piping on an HXA, which is air cooled, you can carry that oil out and have problems. And the machine's smart enough to know it doesn't have oil because it's got an oil level sensor in it, or switch, if you will. It's also looking at oil pressures. It knows if it's low on oil and it won't start. So the screws don't have an oil galley or sump in the compressor itself. The oil is just in circulation through the pipes and through your evaporator barrel and the condenser section. So they're both screw and scroll. They're both sensitive to oil level, but in different ways, if you will, because they're managed completely different. So I don't know if that answers your question or not.
Hopefully so. I'm going to pop one of these poll questions up again while I'm asking you questions, Doug, just so we can get them all in so everybody can get their hours.
Sure.
This one's going to be sort of a repeat, just to make sure we got it. In face split applications, which is proper? I'll pop it up on the screen for you while I keep talking to Doug. Doug, Juma asks, if hot gas bypass is the old method of capacity control, what is the new method?
Well, the new method of capacity control, from a big picture, is digital scroll compressors, multiple compressors in the same circuit. What's kind of replaced hot gas bypass is what's called a minimum load valve, which is essentially doing the same thing. We're introducing hot gas into the evaporative section. So it does the same thing, different name. We accomplish it in different ways now. The screw chillers, it's a solenoid valve that opens up, and we inject the hot gas right into the evaporator barrel. Some of the other chillers were using a minimum load valve that's similar to basically the hot gas. We're using on the little condensing units, a little 7.5 through 15, 20 ton chassis units. We're using the raw valve. The raw valve is a hot gas bypass device that doesn't require hot gas piping all the way over to the evaporator. It's all done right there at the unit. And if we have time, I'll bring a picture of that up if you're not familiar with it.
So would hot gas bypass, minimum load control valve, and raw device be 3 separate things, or is raw the same as one of those 2?
Well, they all accomplish the same thing.
Right.
They pulse load the evaporator, yep, but they're all different in construction and components.
Okay, fair enough. Juma asks, how, let me read this here, it's a little bit of typo, how liquid lift lost power affects the efficiency of a VRF system at part load? Oh, he reworded it, never mind. Let me read the better wording one. How liquid lift power might increase condenser temperature and prevent chiller from working at full capacity. Apparently it's 2 different questions. Okay, my bad.
Well, liquid lift, excessive liquid lift will reduce capacity because the horsepower of the compressor is used up trying to push the liquid uphill. Okay, so it doesn't. It will increase the temperature of the compressor. That's a possibility because we're using a lot of horsepower and not pumping the refrigerant around like we should. So you lose capacity. Is the main result is you lose capacity because the horsepower is used up trying to get that liquid uphill. So maybe that's probably easiest to leave it at that.
Yep. Chun asks, is one control solenoid enough for multiple evaporators?
It depends. So we look at face area of the evaporator coils. We look at line length. We look at a lot of different things to decide if we need a solenoid valve period in a single circuit. And I'm of the opinion we always need a liquid line solenoid valve. How many you need, it depends on what you're doing. We can drive up to 4 solenoid valves with 38 APDs. Typically you use 1 or 2, but in larger jobs, we need to shut off part of the coil at low load so we have proper velocity through the coil. So you may be up to 3 or 4 liquid line solenoids. So it's really dependent upon the evaporator section you have and its size and tonnage of equipment. But we'll say 1 to 4.
All right, Juma asks, why are we charging small systems by superheat while charging chillers by subcooling method?
Well, the difference of subcooling charging method versus superheat charging method really is all about the metering device. If you've got a fixed metering setup, fixed piston or capillary tubes, then you charge by superheat. Because we got to get the right amount of refrigerant into the system in order to get our superheat in the evaporator coil at the right point. Anything else has TXVs or EXVs on it, and if you're going by a chart, they're always going to be subcooling, because the TXV is doing the job of monitoring and taking care of the superheat in the evaporator section. So we go by subcooling in the condenser coil to make sure we've got enough available refrigerant in the system for the TXV to do its job under whatever capacity is available. So really subcooling superheat's based on the metering type. Weigh-in charge is another way of doing it, because we can't get the machine fully loaded, and it's the only way you can use a superheat chart on a fixed metering device or a subcooling chart on a variable position metering device. The only way you get it on chart and use the chart is at a full load, 100% full load. A lot of rambling there. I hope that makes sense.
No, it's good. Mark asks, can you use 1 filter dryer ahead of the solenoid in lieu of 2 after?
Sure.
That's the shortest answer you've ever given on anything I've ever asked you, Doug.
Yeah. I know.
Okay.
Yeah, you can do that. You can use a single one. You don't have to have one for each evaporator or circuit.
All right. Lance asks, does a standard commercial split system have all 3 types of lines, suction, discharge, liquid?
Well, yes. Yeah, so any system will have all 3, but a condensing unit with compressors in it will have a liquid line connection you have to install in the field, and a suction connection where you have to install the suction line in the field. There is discharge piping, but the discharge piping is internal to the unit itself. Whereas a condenser, non-compressor bearing, that's going to have a liquid line connection that you need to connect the liquid line to, and a hot gas line connection. The suction line will all be down at the chiller or whatever you're connecting it to.
And really, I mean, you have 4 lines between the 4 major components of evaporator, condenser, compressor, and metering device. I mean, there's a piece of pipe between each of those 4 major components. Although I don't know what we call the pipe between the metering device and the evaporator. It's so short, no one ever gives it a name, I don't think. But
well, the distributor tubes are what they are. You after your metering device, you go into the distributor and into the distributor tubes, and that's not something you modify or change in the field.
Right. One last one, and I think we need to, let me close this poll so we can go back to the slide that Mark wanted to ask about. Mark was asking about the slide called liquid line requirements that we were on, and he's asking why have a drop solenoid instead of 2 capacity control solenoids?
Where was that? Was that here?
That one has the drop solenoid. Yeah, that's probably the one he's talking about. why have a drop solenoid instead of 2 capacity control solenoids? So instead of having that one on the left,
Right.
why not have 2 in front of each TXV is what he's asking, I think.
You could do it either way. It doesn't matter, but the drop solenoid valve is really to prevent any type of migration in the off cycle on either circuit. But you could take this and put it down there. You could do that, and then that would open up for stage 1. This would be stage 2.
All right. Let me throw one more poll question up, and then we're going to move along here.
Yeah, let me back up on this one too.
Wait, I already launched it, so no one can see what you're seeing at the moment. Everyone answer quickly so Doug can go back to the slide. My fault. Doug's going to assist you with your commercial piping sizing and design if you provide one of these 3 things: a drawing with a proposed piping layout, $200 in cash, or a growler from Greenbush Brewing. Chances are he would do it for 2 of those.
Yeah, definitely. I don't need the cash, but yeah, let's say 2.
Everyone answer that real quick. It's basically a gimme to make sure you're still alive, and hence makes so I can prove that you were on the webinar. And then I'll close it here in 10 seconds, and we'll go back to the slide Doug was looking at. Sorry about that, Doug. I clicked it, and then you said wait.
No problem.
All right, I'm closing it in 5 seconds. So answer. 3, 2, 1. Okay.
All right. One of the other things I wanted to add here, since that question did come up, the drop solenoid in this position, now we don't do it. We don't recommend it with our condensing units or condensers anymore. We used to a long time ago with our 38AH units, and prior to that, the ADs and AEs for all the carrier people that worked on the old units. The drop solenoid was used for single pump out control. Okay, so when we were done with, when circuit 2 was satisfied and then circuit A satisfied, the drop solenoid would close, and we essentially would pump out all the refrigerant in the coil in this area here, and some of the suction line down to what used to be 27 psi gauge. We'd do a single pump out. That way all the refrigerant was stored ahead of the liquid line solenoid valve here all the way back to the condenser coil. So it was a way of managing refrigerant on the low side, so we didn't have flooded starts, and we had better, actually a little increase in capacity because we had an instant liquid seal at the expansion valve, so the liquid was literally right here and ready to go. So it didn't take 5 minutes run time to develop your refrigerant pressure differentials and get a good column of liquid in the liquid line. So, but drop solenoid location would have been like this back then. But again, we don't do that nowadays on any of our condensing units or condensers. So hopefully that may have helped out there. All right. What else? Tons per circuit. That's something you won't see unless you're looking at your coil selection or coil builds. Tons per circuit, let's say in this case, what do we have? We got 1, 2, 3, 4, 5. We got 5 distributor tubes going into feeding this coil. So we got 5 circuits, okay? If we have 5 circuits and we have a 10-ton coil, you would take that 10-ton coil and divide it by the 5 circuits, which would give you what? 2 tons per tube. When you hear tons per circuit, this is what we're talking about. How many tons of refrigeration effect are we doing with each distributor tube? And we have a minimum on that. If you got 3/8 tubes in the coil, or 1/2 inch, what we use most all the time, it's 0.4, 0.5 tons per circuit. The older R22 systems with 5/8 tubes, we looked at 0.6 tons per circuit. Why this number is important is if you fall below these levels, your suction gas velocity through the coil is too slow, and we won't entrain oil through the evaporator coil, and we'll end up oil logging the coil. So we always have to watch out for our tons per circuit. So in conversation of coil selections and piping and all that, it may come up sometimes where I get submittals sent to me and coil selections, and I reject it because the tons per circuit are too low, which means you got to reselect the coil and get the distribution changed. Okay, so just in case that ever comes up when you give me a call on something, if I'm doing some piping for you, I'm looking at the coil selections, which, you know, again, we review all evaporator DX coil selections commercially. That may come up sometime, tons per circuit. So just a good slide to show you what that means and what that's about. Okay. Again, shows a distributor nozzle right here. Always make sure that your distributor has a nozzle in it. The nozzle will have a letter and number stamped on it that you'll be able to see. The actual letter is the outside diameter of the nozzle, so you know what nozzle to get to fit in what distributor, because we have, you know, you got 5/8 distributors, 7/8 distributors, inch and an eighth, inch and 3/8, you know, inch and 5/8 distributors, and you got to have a nozzle that fits, it slides in here. So this fits and slides into a seat, and then there's a C-ring that holds it in place. So we have the outside dimension that is indicated by the letter, which I'll show you, and then the hole through the center of it is your numbers. You may have a G7, a G11, whatever, nozzle, and I'll show you what that all means in a second. But what that nozzle does is it takes the refrigerant coming off of the TXV, and if you think about a garden hose with a spray nozzle on it, that's kind of what it looks like here. It doesn't go from liquid on this side straight into a vapor state here. It doesn't do that, otherwise we wouldn't have superheat control in here either, but it's a spray that hits here. So we're taking that spray and we're taking it through the nozzle, so we hit the center of the distributor, and you can see how if we centered that spray and we hit this, we get even distribution into each one of our distributor tubes. That's what the nozzle is all about. It's kind of like a pre-metering device, if you will, prior to the distributor. So we want to make sure that that spray is sprayed in to the distributor evenly, so each and every tube is getting equal amounts of refrigerant. So that's what that's all about. A nozzle can make or break a system. You know, if it's oversized, you get terrible control. If it's undersized, we starve it. It messes with your superheat. It does all kinds of things. So nozzles are very important, and that's something that we look at in the coil selection. We'll say, okay, you got this coil. Your tons per circuit's good. You need this nozzle and this TXV for that particular condensing unit. And again, we do all this for you. You know, you don't have to go through all the math and the engineering on it. Okay, and here's an actual Sporlan chart for nozzles. So here's your letters, and there's the bore through it, the diameter hole that's through the nozzle. And you'll see there's only so many letters. If you have a J in the letter, you come across, and the outside diameter is a 1/2 inch. So if you had a 1/2 inch distributor, you would need a J nozzle. Now you could have a J3 nozzle, which will give you 3.6 tons with R22, 4.3 with R410, or you could have a J4, which your tonnage goes up. You can have a J5. So basically what's happening is the hole through the center. So again, the number is the hole right here in the center of the nozzle. The letter is the outside diameter, so the nozzle fits inside the distributor. So as the number increases, so does the tonnage. And as the letter changes, so does the diameter, outside diameter of the nozzle. So a J fits a 1/2 inch. A 1/2 inch distributor. A G nozzle would fit a 7/8 distributor, and then an E nozzle will fit a 1 inch. C nozzles for an inch and an eighth, kind of, so, you know, so forth and so on here. Okay, so that's what this nozzle deal is about, the letter and the number. Again, letter designating the outside diameter that governs what TXV it actually fits in, and the number is actually the tonnage of that particular nozzle. So hopefully that all makes sense. Okay. So any questions on that? I guess before I move off. We're just about done here. I think we got a couple slides left.
Some reason I can't get the question box to pop up. So I'm going to say none for this exact moment, and I'll keep trying to fix the question box.
I think I got 3 or 4 slides left, so we'll be done here. And then we can go back to questions. All right. 38 APDs and APSs. So we've got another device out there that goes in the liquid line. And we use this for various things. We call it long line application check valve assembly. Okay. And we have to have this assembly on each liquid line. So if you got an APD, you're going to have 2 liquid lines. If you got an APS single circuit, you have 1 liquid line. But if you have applications that have more than 100 feet of liquid line pipe on it, then you have to have the long line check valve. If you have a little 25 to 30 ton dual circuit unit and the evaporator is located higher than the condensing unit and the linear line length is more than 55 feet, you got to have one of these valves. Okay, you want to put these, install these as close to the condensing unit as possible. So as soon as that liquid line leaves the stub on the condensing unit, as soon as you can get this in here, the better off. So, and what it is an anti-migration device. It prevents refrigerant to migrate back to the compressor during the off cycle. And, you know, obviously dilutes the oil, all kinds of bad things. So, flow on this guy would be, in this case, right to left like that. Okay. What this is a relief check valve. So if the differential on both sides exceeds 50 psi, then it will relieve back. You know, just in case we got gas trapped between here, liquid trapped between here, and of course the TXV or solenoid valve over here. Okay. So if you put one of these on, it does not substitute the liquid line solenoid valve. You still need liquid line solenoid valves as well. Okay, but you may see this. Well, how do you know when to order it? That's done for you at the TM level, at your sales TM level. So when they select the unit, they've got an electronic selection program. You know, they'll say, okay, you need a 38 APD 030, and it'll pop up long line check valves required. So they'll select them for you, and that'll be part of the package when they sell you the unit. Okay, among other refrigeration specialties, coil, air handler, whatever. Okay, so just know that's what this is. That's what it looks like. That's what it does. This is actually a cut and paste out of the book, out of the installation book. So it will tell you all the same thing, all this information. And why did I put this here? I don't know. Put this here for a reason. Maybe to circle back around, just to say again, going back to the split system condensing units, I guess probably since I was showing you this, went back to this slide again as a recap. Model number, tonnage, circuit A, circuit B. How long a pipe run do you have? You bring these numbers together, and then there's your pipe sizes. Again, shaded or bold is going to mean double suction risers. Shaded or a T or an asterisk is going to be down in the notes on condensers, and they will tell you double discharge risers are needed if certain things are in place. Okay. This is another chart off our smaller chassis units, the 38 AUZ 6 ton or 07s through the 025 20 ton units. And here, there's more information on this chart. The engineer that put the chart together put everything on the chart, and it just stayed this way. This kind of information is in the background of these charts. But this particular engineer, John Farrell, he's no longer with Carrier, but he put this together years ago, and it's got all kinds of things in it, but it works the same. So you find your model number. Let's say we got a 38 AUZ dash, which it could be a AUZ, D, or a B, what have you. But you look at this, a 12, which is a 10 ton. It gives you a liquid line, which is 1/2 inch at 0 to 25 feet. You go out here at 50 to 75 feet, you could use a 1/2 inch liquid line, or you could use a 5/8 liquid line. A 1/2 inch liquid line would give you an equivalent liquid line pressure drop of 2.9 degrees. A 5/8 would give you a 0.8. Well, a 5/8, you're going to be more efficient at a 0.8, it's less of a pressure drop, right? Doesn't take as much horsepower off your compressor. But you got to watch it with a 5/8 if you're going out too far on the piping. You got to look at your weight of refrigerant per ton. So, but they give you options, so you can go to 1/2 inch, or you could use 5/8. That carries out until you get out to 175 to 200 feet, and here 5/8. So, and again, your pressure drop, as you can see, 5/8 here is 0.8 when you're at the 50 to 75 foot. And as 5/8 continues out, you can see your pressure drop increasing all the way out here to 200 feet, where your 5/8 is going to give you a equivalent 2-degree pressure drop, which is fine. That's good. Remember with that 2-degree number, we want to stay around there, a little bit below. You can go a little bit higher. That's fine. This chart also gives you a max lift. Okay, remember that's pushing the liquid uphill if the evaporator section's above the condenser. In this case, 0 to 25 feet and a 1/2 inch liquid line, max lift is 25. So you can just kind of see how all your max lift is out here with your different pipe and what have you. So, and then he also has it here. You had it here in feet, and you got it here in equivalent temperature. Okay. Suction line right here, same thing, 0 to 25 foot, 1.125. 1.125 carries you all the way out to 75 to 100 feet. And at that point, we're at 2.8 degrees equivalent pressure drop, which is starting to get to starting to be a lot. If you ran this, you probably would come out to anywhere from a 1 to 2% loss of capacity, not much. But he's got it in the chart here where now you can start going to 1 3/8 and get back down to an equivalent 1 degree pressure drop in your suction line. Okay, so that's how that kind of works out there. So he's got a lot of different stuff in this chart, all in one chart. So also we got a charge chart in here for 25 feet of pipe. So that kind of tells you what we got going on here. Okay, so kind of different look at pipe sizing chart. And I talked about the preliminary charge in a unit. These are for the APSs and APDs. Again, when you look at that chart, let's say you got an APD 50. Circuit A needs 22 pounds, circuit B needs 26 pounds. Well, this is if you have 25 feet of pipe only. If you got more than 25 feet of pipe, you need to start calculating the additional feet of pipe. Plus, you also have to look at the weight of refrigerant in the evaporator coil. Because again, in the commercial coils, we're talking about more refrigerant than in the res coils. And even in little res coils, you'll see a chart in the evaporator coil manual that will actually increase your charge. There's actually a weigh-in charge for the evaporator, but it's very little. It's like maybe a couple ounces here, a couple ounces there. It's not much. But, commercial machine's much larger, and it makes a bigger difference in refrigerant charge. All right, so I take it this is the end of my slide tray here. So any questions?
Yes, I'm going to throw up this last closing quiz question so people that need to leave can go ahead and check out and leave and still get their hours. So we missed a question that earlier when I couldn't pull the screen up. It was from Michael. He asks in regards to tons per circuit, are you adding the tubes together to get the total tonnage?
You could go that direction. if we know we have a 10-ton rated evaporator, and this is all when we build the evaporator. So, you know, when we build an evaporator, we actually build the number of rows, the number of fins per inch, the face area. And once that evaporator is built, the builder program spits out a tons per circuit. So if I know I got a 10-ton evaporator, like I said before, and I've got 5 distributor tubes, I can take my 10 tons and divide it by 5 and figure out my tons per circuit. You could probably work it backwards. You could probably count up the tubes and get a rough idea of where you're at. If you figure it out, you know, if you figured them at maybe a ton per circuit, you know, it's going to be a give or take. It's not going to be real accurate, but it'd be a rough estimate of how many tons the coil is. Now, if you use a ton per circuit, just a rough estimate, then that's also saying you have 1/2-inch tubes in your coil. So if you got a 1/2-inch tube coil, you counted up your feeders, you could probably use a ton per feeder tube and be close. You may be off, but you'll be fairly close to how large the coil is, if that's what if that's why you're asking the question.
All right. Mark asks, isn't the job of the solenoid valve to stop migration? And if yes, why do we then need long line check valves as well?
Well, the job of the solenoid valve is a couple reasons. It's to stop migration, and liquid line solenoid valves actually increase efficiency a little bit because it holds a column of liquid behind it. So the second it opens, that column of liquid is available for the TXV. And we start feeding and start getting refrigeration effect off the evaporator. If we didn't have the liquid line solenoid valves, you're going to have off-cycle migration because of the varying temperatures between your evaporator and the airflow over it, and the condenser's ambient and piping, et cetera, right? So now the unit starts up and it may run for 5 minutes or so, I don't know, 3 minutes or so, before we actually start developing a column of liquid in the liquid line, because we may have had a migration somewhere. So it's actually about preventing off-cycle migration, as you said, but in addition, it can actually help with efficiencies as well. The long line check valve is in addition to a required liquid line solenoid valves, because we know that we know that solenoid valves will leak in the off cycle over time. So it's an added preventative measure when we get out to certain line lengths and or if the evaporator is above the condensing unit.
All right, I think that is all of the questions we had. From a housekeeping standpoint, if you needed PDHs and you requested that when you registered, we'll grade these quiz questions and we'll get those out to you. I'm gonna just let you know it's probably gonna take like 2 weeks. We have such a massive backlog of all of these. But we'll definitely get them out to you. If for some reason you need to renew your license before then, let me know and we'll manually take care of yours. But otherwise, in the next couple weeks, you should get an email with your certificate if you need the PDH certificate. If you have any further questions, you can hit me or Doug up. Just reply back to the all the confirmation and registration emails you got. It'll go to my email, and I can always rope Doug in if need be. And then beyond that, if anyone wants to watch the recording, I can send you the link to the recording if you have a coworker that needs to see this kind of thing. Anything else, Doug?
No, just want to thank everybody for joining us today, and hope this was helpful for you.
All right. Thanks, Doug. Appreciate it, man.
You bet. Everybody take care.